Compilation and type systems session. I'm Charles. I'm an assistant professor at University of Wisconsin-Madison. We've got 5 great papers lined up for you today. And the first one will be presented by Jungyao Lin from Carnegie Mellon University. Jungyao is a PhD student, and one thing you should know about him is that he is actively on the job market for industry jobs. So, Jungyao, take it away.
New batteries, I think. I don't know how to use this.
Oh, okay.
Oh, it works. Now it works.
Now it works? Okay, cool. All right, great. Thanks everyone for coming. And so in this talk, I'd like to present our work in formally verifying asynchronous data flow compilers. And this is on behalf of my awesome collaborators, E and Emiliana from the University of Maryland. So in a few sentences, our work is about designing and building a verified compiler in Ling, targeting these novel architectures based on spatial data flow, which is a historically difficult target to correctly compile general purpose program into. That is programmed with irregular control flow and memory access patterns. And in our verification, we also try to use modular proof techniques, and we also leverage a front-end capability type system to guarantee the race freedom of the compiled data flow circuit. So what is the motivation behind all this? This might be a bit of a cliche, but computing systems today are increasingly heterogeneous. So on one of the spectrum, you have CPUs, which are very programmable and flexible, and GPUs, which are great for massively parallel workloads like graphics and machine learning. But they waste a lot of energy in moving data around and are usually power hungry. On the other hand, domain-specific accelerators, or ASICs, are fast and energy efficient. However, they're wired to perform a fixed set of tasks, like for multiplying matrices, and the application domain is relatively fixed, like for writing ML kernels. So it's a natural question to ask whether we can find a balance in the middle to allow general purpose programmability, like CPUs, while achieving energy efficiency and performance close to ASICs. So our work targets 2 lines of work in architecture that are pursuing this goal of enabling hardware acceleration for general purpose programs. One such area is reconfigurable data flow architectures, or RDAs, in which you have an array of processing elements, or PEs, in the hardware, and you can configure each PE to function as a high-level operator for arithmetic or accessing some shared memory. These are similar to FPGAs, but the operations are like at the word level instead of logic gates. So one of the benefits of RDAs is that you can place these operations close to each other and spend most of the energy in compute instead of moving data around. And as demonstrated in prior work, Riptide, such locality can enable sometimes 100 times better energy efficiency on certain applications compared to off-the-shelf low-power CPUs. In a different line of work, people have been working on compiling high-level programs like in C to hardware designs, or in other words, doing high-level synthesis. While traditional HLS approaches try to find a static execution schedule for the source program and then encode that in the hardware as a state machine, It has been realized in recent work if we allow components of the program to be data-driven rather than following a static global schedule, we can achieve much better performance on irregular control flow. And this approach has been realized in HLS frameworks such as Dynamatic. So despite coming from slightly different communities, these two approaches share a key compilation challenge. And that is how to bridge this gap between the more general purpose workloads with irregular control flow and memory access patterns and the actual hardware with abundant parallelism that we want to utilize. And a promising solution found in this prior works is the abstraction of asynchronous data flow. So this representation has two important benefits. First is asynchrony. So in an asynchronous data flow circuit, each operator or gate can execute as soon as input data is available without following a static global schedule, which can drastically improve the performance in programs with irregular control flow. The second is that by representing the program in this pure data flow form, the hardware can be configured to maximize data flow locality and achieve much better energy efficiency. Therefore, in the compiler pipeline, we can compile the source program into a data flow circuit, which I'm referring to as the data flow compilation here. Then the data flow circuit can be much more easily mapped to an RDA for execution or further lower to hardware designs for HLS. However, the benefits of asynchronous data flow becomes challenges for correct and efficient data flow compilation. So the semantics of this data flow circuit can be thought of as a large collection of concurrent processes, and they would pass messages through these channels denoted by edges in this graph, along with potential concurrent accesses to a shared memory. So an incorrect compiler might introduce annoying concurrency issues like deadlocks and data races that are not possible in the original sequential program. But at the same time, the compiler has to soundly extract parallelism in the original program as much as possible, because if we overly synchronize the data flow circuit, we would not be able to utilize the parallelism in the hardware. Larger applications in this domain may scale to hundreds of asynchronous and parallel data flow operators. So trying to debug a data race or deadlock caused by the data flow compiler would be a nightmare. So in other words, the central goal here is that we want memory consistency, but without sacrificing the performance and parallelism. In this work, we hope to use formal verification to prove the absence of these issues ahead of deployment. In particular, we design and formalize a data flow IR and compiler called Wavelet, built using the Ling theorem prover. And we prove that the compiler produces an equivalent data flow circuit along with good properties such as deadlock freedom, data race freedom. And importantly, our compiler and proofs are also structured in a way that enables an important optimization of data flow pipelining, which supports more parallelism in the data flow circuit. So let's see how Wavelet works at a high level. The source IR is an imperative language that we're calling LLET start. The user has to explicitly annotate capabilities and fences for array accesses. And our type checker then uses these annotations to extract memory dependencies as explicit data dependencies, and elaborates the source program into the second IR called LLET. So the reason that we need these memory dependencies represented as the explicit data dependencies is because in the end, the data flow circuit is asynchronous and does not have any control flow built in. And the operator can only synchronize through data dependencies in our hardware abstraction. We then pass the elaborated LLET program to the core passes of our data flow compiler, which converts LLET to a simple data flow calculus that we define called LFlow, where we convert basically all the imperative control flow to pure data flow. And in these core passes, we first compile each function, and they are modularly linked in a separate pass into a single data flow circuit. And in the final pass, we perform some optimizations and rewriting to make the data flow circuit smaller and more performant. So in wavelet, we formally define and verify the two core passes in the Lin theorem prover, proving semantic preservation and a property that we call determinacy, which basically rules out data races in the data flow circuit. And some of the assumptions of our determinacy theorems are validated by the front-end type checker through SMT solving. So in this talk, I'm just going to give two high-level examples of the two crucial passes in our pipeline, which are the verified core control flow conversion in the middle and the capability type checking in the front end. So let's start with the pass that we call control flow conversion. So this is the data flow circuit that I've been showing as an example. And this was actually compiled from this simple function on the left, which kind of computes sort of a dot product between two arrays B and C. And it's written in a tail recursive form for a simpler correspondence. So the circuit on the right might seem a bit complicated, but let's see how the different components here correspond. So the function parameters correspond to these carry operators at the top, which takes in initial values for these parameters and also merges any values from tail recursive calls. So you can see there are some back edges from rest of the circuit to these two operators. And the branch condition is computed by this comparison operator. And the result is passed to some of the triangle operators below, which activates the circuit corresponding to the correct branch. Then we have the true branch, which consists of some memory loads and some arithmetic operators. And finally, the false branch just corresponds to this output channel R, but it's also gated by this triangle steer operator, depending on the branch condition. So we define this compilation pass in Lin in a way that's similar to this correspondence, and we prove a forward simulation theorem that the data flow circuits simulates the behavior of the imperative source program. In other words, if the imperative source program has some trace of memory interactions, then the data flow circuit can also execute in a way that exhibits that trace. However, forward simulation doesn't rule out additional bad behaviors on the data flow side. For example, what if the data flow circuit has a data race and can have a different result if the memory operators are scheduled differently? And the way we prevent that is by proving something called determinacy, which basically means that the data flow circuit needs to have a deterministic result. To see why that's a problem, let's tweak our example a bit. First, let's remove the return value here and just make it a unit. And we also remove this accumulator argument R here as well, and replace it instead with a memory load and store. So we're basically storing and updating the results in the memory instead. But this circuit is a bit problematic because there is an implicit read after write dependency enforced by the sequential control flow that sort of gets lost in the compiled parallel data flow circuit. So the load in the next iteration may happen before the store in the previous iteration has finished. And one of the solutions for this issue is to add an extra data dependency between memory operators. For example, here we can introduce an additional backedge from the store to the load to send a memory synchronization signal. So that load in the next iteration will always wait for the store in the previous iteration to finish. So now the question is, how do we sort of manifest this extra data dependency in the source program as well, so that the programmer can more accurately and soundly control how the synchronization should be done? And our solution is to use a capability type system in which we annotate each function in the source program with the required memory permissions. For example, here f needs to have the capabilities for accessing arrays B, C, and the pointer R. And the reads and writes of these arrays will consume these permissions, which are affine. And when you need to reuse them, you need to add an explicit fence annotation to kind of recycle the used permissions. And these fence annotations will then later manifest as these explicit memory synchronization dependencies through an elaboration pass that I briefly mentioned before. So I talked about two main pieces of our data flow compiler. Now, how do they fit together to formally guarantee the correctness of data flow compilation? So with the same example, let's call the input imperative program D, and on the right, we have the compiled data flow graph after control flow conversion. And if we take their semantics, we've mechanized the theorem that the source program is simulated by the compiled dataflow circuit. That is, the dataflow graph has at least one behavior trace that is equivalent to the source program D. For the determinative part, what we did is that we formalized sort of a dynamic capability checker in the semantics. So guard of D here is the same semantics as D, but with capabilities dynamically checked in the semantics. And the semantics would get stuck if suitable capabilities is not satisfied during execution. So the progress of this guarded semantics is validated by our type checker, meaning that it checks that all operations during execution will always have the suitable capabilities on any inputs, and this is done through SMT solving. And on the dataflow side, we can apply the same capability checker, and we prove that the simulation is congruent with respect to this guarded semantics, so we can directly use the simulation theorem above to prove that the guarded semantics also have a simulation. And then by sort of propagating the progress of the imperative side to the dataflow side, we can prove that the dataflow side is also sort of has this progress property in the guarded semantics, and we prove that this implies that the dataflow circuit is race-free and deadlock-free. So let's zoom out from the details and talk about the evaluation. So in the evaluation, we compared our dataflow circuit wavelet with two existing unverified dataflow compilers. The first one is Wavelet, which is a general-purpose CGRA focused on energy efficiency mostly. And also LLVM circuit, which is in general a collection of IRs and compilers based on MLIR for hardware design. But we're comparing with a specific compiler pipeline in it that does dynamically scheduled HLS. For Riptide, we simulate the resulting dataflow circuits and compare the performance and size of the resulting circuits across 10 benchmark programs. And the result is as follows. So for both graphs here, lower is better. So as one bit of a detail, there's an optimization called streamification in Riptide that we do not support yet. So for one category, we disable that for a sort of more apples-to-apples comparison. Overall, we are about 1.7 times slower than Riptide and producing dataflow circuits that are about 2.3 times larger without this streamification optimization. And the main difference here comes from different memory synchronization strategies where we use a more explicit mechanism for synchronizing potentially different conflicting memory operators, which leads to larger circuits and slightly slower speed. But I do want to note that we did actually find some bug in the Riptide compiler on one of the programs that would cause a data race in the dataflow circuit. So this trade-off is meaningful in improving the correctness guarantee. The second comparison is with circuit in dynamically scheduled HLS. So here, for both wavelet and circuit, we're compiling the source programs to dataflow circuits and then lower them to RTL. We're comparing their execution time estimated from RTL simulation as well as the resource usage when targeting an FPGA. So in average, we're about 1.2 times slower than circuit, but we use less resources because of a different choice of control flow operators. Yes, the last slide. Yeah, thanks. So in conclusion, Wavelet is a dataflow compiler with its core passes formally verified in Ling, and we use the capability types to guarantee the determinacy of the compiled dataflow circuit. And our evaluation shows that our compiler produced circuits that are about 1.4 times slower on average than existing unverified dataflow compilers. And you can find out more about Wavelet from our paper and GitHub repo. Thank you so much.
Thank you so much for the talk. In the interest of time, we're going to move to the next speaker, who is Joey Velez-Inorio from the University of Pennsylvania, who is going to be telling us about compilation to recurrent neurons.
Should I use that mic?
They took that one, I guess.
Yeah, this one?
Sure.
All right, hi everybody. Thanks for being here. This talk's going to be about a future that I see for how we could be programming neural networks. And to start, I want to begin with some observations about why I think programming languages are important. The first, I think, is pretty obvious, which is that they help us build stuff. But the second, I think, is more subtle, which is that they also help us understand things. And the crux of my talk and my position is that I think we've made so much progress when it comes to programming neural networks on the first thing, on building things, but maybe not so much on the second. And I'm interested in a future where we get better at that problem. And to kind of make this point a bit more clear, I want to take a brief kind of digression into history. So this computer on the left is the IBM 650, and the code on the right is implementing a matrix multiplication, but people back then would actually write in machine code that looked like this. And what's interesting about the machine code is that it was certainly good enough to help you build things, but maybe relative to the languages that we have today, it wasn't so good at helping us understand the IBM 650. And by understand, what I really mean is your ability to predict and control the behavior of some system. And so with higher level languages, what they're allowing us to do is not only build stuff, but also predict and control the behavior of very, very complicated machines. And the necessity of building languages, not only or writing languages for building things, it wasn't obvious that you also needed to build languages for understanding things. And there's a very famous exchange now between John von Neumann, who you see on the left, and John Backus on the right, where they're having a meeting in the early 50s, around when the IBM 650 was around. And John Backus is introducing the Fortran language to von Neumann. And famously, after the meeting, von Neumann says, in response to the Fortran programming language, why would you need more than machine language? And the machine language he's talking about really is the machine code that we saw on that previous slide. And so this wasn't a fringe view that von Neumann had. This was really a commonplace perspective on whether we really needed high-level programming languages, or rather languages for understanding these systems. And the main reason why this was the case was for two reasons. One, it wasn't clear you could even build compilers for these languages. And two, even if you could, were you going to emit efficient code? And that was a really big problem for a long time. One last thing about this is that the irony in the statement is, of course, that John Backus would go on to win the Turing Award precisely for his work on the Fortran programming language. And the reason he got the Turing Award was because, one, he solved some very hard problems with generating actually usable code from a high-level programming language. But I think the other reason why he got the Turing Award is that Fortran really is a language for understanding things. It's not just about building things. And the reason the language is useful for understanding things is the presence of more abstract data types for thinking about your program. So instead of thinking about everything in terms of binary, you could think in terms of arrays of integers or floating point. And this is a really important point that I'm trying to make in the talk, which is that the presence of these abstract structures make it profoundly easier to understand a system. So in contrast, right, if you're writing machine code, you have to sort of massage every algorithm in your head into a function that looks something like this: transformations over a machine state. But with Fortran, you had the ability to think in more abstract terms. And it's the availability of these discrete structures, both in Fortran and in languages that would follow. Oh, I have to do like an interesting thing to make this work. That would make it easy to understand systems. And so now this brings me to my point with respect to programming neural networks, which is that I think if I could condense in one slide the history of programming neural networks, it's really been about making it as easy as possible to write down functions that look like this, and as easy as possible to learn functions that look like this. But the issue with functions that look like this is that they're not necessarily useful for understanding the underlying network. And I think traditionally we think of this as maybe a problem for the neuroscientists or for the machine learning people. But I think actually we have a very good toolkit in programming languages for thinking about how to build abstractions on top of all kinds of things. And so the position I have in my talk is I think we should be building languages that introduce the same kinds of abstract discrete structures we're used to in our ordinary programming languages, but with respect to programming a neural network. And I don't mean the whole thing, so I don't think like the whole neural network should be some like discrete algorithm, but at least parts of the behavior of these systems could be and certainly can be specified by discrete algorithms. But the core problem with doing this is that neural networks need to be composed of differentiable functions, and functions that look like this aren't necessarily differentiable. And so if you stick it inside of a neural network in your favorite programming language for building a neural network, what will happen is that learning will break because you can't compute the derivatives necessary to get learning to work. But I think ultimately this is a compiling problem, and we have tools for thinking about how to compile from high-level programming languages into various kinds of targets. And so to study this problem, I basically introduced this small calculus called Cajal, which is a linearly typed lambda calculus with just Booleans, natural numbers, and higher order functions. And the idea is to basically isolate how we could build a higher level language for programming neural networks where you're free to use conditionals and iteration wherever you want. And as a concrete example, here's a kind of program that you could write in the language. So here what we're doing is iterating a Boolean operator over some value. But to understand the syntax, you basically, to specify an iteration, you need to give a base case. In this case, the value true, which I denote with TT. And then what transformation you apply during the iteration. In this case, the not operator. And then specify how many times you want to iterate. And in total, what will happen is that if you run this program, it'll iterate the not operator over the base case, or the base value true, and then return true. Now, the most important part of the language design is the fact that this language is linearly typed. And in the paper, we talk a lot about the distinction between linear typing and ordinary typing, but for now, a perfectly good intuition is that what linear types are tracking in your program is that the variables in your program are used exactly once. And it'll turn out that this syntactic notion of linearity is intimately related to the notion of linearity from linear algebra. And as a consequence, a good intuition for what we're about to do is that it's going to be the case that each one of the programs that you can write in this language can be compiled into a matrix of real numbers. And because it's a matrix of real numbers, it's differentiable, and you're free to stick these matrices wherever you want inside of a neural network. And so in some sense, what we're going to be doing is compiling algorithms into little circuits that we can place inside of neural networks to act as a kind of sub-circuit that does something for the network. And so the example that we just went over could be linearly typed precisely because every variable that appears in the program is used exactly once. So what we end up doing is we can formally specify this relationship between linearly typed programs and linear maps, more specifically multilinear maps. But a sort of 95% correct intuition for what we're doing is what I already just said, which is that every program in the language can be turned into some kind of matrix of real numbers, and because that's a sort of perfectly fine object for programming languages for neural networks, you can stick them wherever you want. Now, one rule I just wanted to highlight, because it justifies the name of the paper, is when you compile iteration over the natural numbers, it turns out that the equations that pop out correspond to the behavior of recurrent neural networks. So these are neural networks that have sort of feedback connections going to themselves. The first two sections of the paper talk a lot about this point, if you're interested in that correspondence specifically. But I think the greater point of the paper is you have a language where every program can be turned into a matrix, and this matrix can be put inside of a neural network. And so we end up checking that this correspondence holds with a compiler correctness theorem. And in short, what we're trying to do in the theorem is check, it's starting from the position of you know how programs behave in the source language, you know how they evaluate and how they don't evaluate. That's a sort of top arrow to the right and top arrow to the left. And based on that understanding, you want to be able to predict what the compiled code is going to do, or that compiled matrix. Right? And if you can do that, then the compiler correctness theorem goes through. And the lemma that does really most of the heavy lifting in this proof is the one on the bottom right, which kind of justifies the intuition that I've been gesturing out throughout this talk, which is just that programs, when they're compiled, actually are multilinear maps, or if you want, just think of them as matrices. Now, the compiler correctness proof tells us that these matrices, in some sense, implement our source algorithms. But what the theorem doesn't tell us is that if we stick these matrices inside of a neural network, it's actually going to be useful. That's a much, much harder notion of correctness. And so to probe that notion of correctness, we do some experiments in the paper. So I'm just going to briefly talk about one of the experiments we did, but we have several in the paper. And for this task, what we're doing is we're going to ask a neural network to transform an image. But if the input image is even, we just want it to do identity. If it's odd, then we want it to apply an iterative blur to the image. So if the input image is a 3, apply the blur 3 times. If it's 5, do it 5 times, so on and so forth. And what's nice about this task is that there's some discrete structure we clearly have intuitions about how to specify. There's a conditional, there's some iteration. But there's also some kind of messier structure that neural networks are quite good at figuring out, like detecting if the input image is even or odd, or applying or learning a kind of iterative blur. And I should also say that this is not meant to be some kind of like engineering benchmark. We're sort of trying to figure out how to build these like weird compilers and then trying to design experiments to like poke at what they can do. And so what you can do to solve this task is you can set up a model where you compile a program from Cajal. And what will happen is that this turns into some matrix, again, that you can just place into a network. But I've highlighted in red the free variables that will eventually be instantiated by the outputs of some other neural network. So what you can think of this as doing is that you're specifying part of the behavior of some neural network, and there's sort of other neural networks supplying the values for even and for blur and for digit. And so what I'm showing here is basically the behavior of 2 models. There are more models that we test in the paper. But for sake of time, I'll just talk about the one that has compiled structure and some naive baseline. And so what you're seeing on the x-axis is just the behavior of the network across training time. The left half has the sort of first 200 steps of training, and then the right half has the first 10,000 steps of training. This decomposition is useful because there's usually a lot that happens in the first 200 steps, at least for these experiments. And so the behavior you want if the network is actually learning to do this task is that it should be that when the input image is a 6, it's even, so it should just do identity. And when the input image is a 7, it's odd, so it should do this iterative blur. And across training time, the TLDR here is just that it eventually does learn how to do the task. I don't have too much time to talk about it, but there's actually a lot of like subtle things in the way that it gets to the solution that are quite interesting. Like it transitions to like a pure identity phase and then sort of gradually integrates the sort of iterative component to the task. And that's very different than what the other models do. And so as a kind of naive baseline, we set up a neural network with kind of comparably simple components to the model in blue, which is the one that was derived from Cajal. But we basically don't have a compiler stringing things together in some clever way. And the long story short here is that it just figures out how to do some kind of constant blur to most images, and it doesn't quite learn how to do the task. But the takeaway here is not that you couldn't solve this task without the compiler. There almost certainly is some kind of architecture that can solve this. But what we were testing with these experiments is whether you can take very simple neural components, string them together using the compiler, using a high-level program, and then use that circuit to solve a task. And so, in summary, the kinds of results and the things that I'm learning from these experiments in the paper, not just from this work, but basically every experiment I've done in my PhD, is that you can certainly, for very small networks, compile sort of simple algorithms into them. And gradient descent is like amazingly good at figuring out that there's this like weird circuit that you've put into the network. And so long as it's relevant to the task at hand, it can find that circuit and use it to solve a task. And so in the time since PLDI, I've been doing this with transformers as well, getting similar results. And I think the thing that I'm most excited about is figuring out how to scale up these ideas for much, much bigger systems. So not just kind of small algorithms and small networks, but how would you compile some algorithm into an LLM with billions or trillions of parameters, and also what algorithm would you compile? So for most of the experiments I've done through my PhD, it's been about compiling something like a sorting algorithm or some kind of reversal algorithm. But of course, LLMs are solving many, many tasks. So what's the right kind of discrete structure? I'm really excited about compiling the kinds of combinators that you find in the standard libraries of functional programming languages like fold or scan. The idea being that compiling those programs as matrices you embed inside of a network, they'll have this kind of generic algorithm for solving a variety of tasks the same way that you can use fold and scan to solve a variety of problems in functional programming. And with that, happy to take questions, and thank you again for your time.
More of clarification than a question. Slide 32 is a 6, 7.
Yeah.
Was it intended?
Oh, no. No, I'm too old to know that was a reference. I guess, yeah, go ahead.
Hi, Harry Goldstein, University at Buffalo. Great talk, thank you so much. I guess the alternative to this kind of thing is to have the neural network output functions and have it solve problems by outputting functions. Can you talk a little bit about why the function being compiled into the network gives us advantages?
Half as much of the data to get the same performance. I mean, that would be crazy, right? But it is basically the result suggested by like every experiment I've done in my PhD, right? But of course, there's problems. There's a bunch of engineering and systems problems that I know I'm going to run into at scale that I haven't had to touch so far in the work that I've done, because I've been mostly working with small networks. But yeah, data efficiency is basically the big engineering value proposition.
Very nice work. And I know your goal is different, but have you thought about going in the opposite direction? Like taking a network and somehow decompiling it and using that as a way of interpretability, right?
Yeah, I used to be very interested in this, and also I remember answering a question from Harry like a couple of years ago, actually related to decompiling. I think, so I have some background. I used to be like a neuroscientist, and I got interested in PL exactly because I thought the techniques could be useful for understanding neural networks. I think decompiling an arbitrary neural network might be completely doomed. But what might not be, and the reason is just that, like, I mean, the neuroscientists have been going hard at understanding neural networks for a long time, and there are some really thorny issues there. And I think the idea that, you know, you can like go into a subcircuit, we should run. Oh yeah, maybe we should run, actually.
We should evacuate.
Yeah. Anyways, it's really hard. So, but it is very interesting, and I'd love to talk about it offline. Yeah.
Let's thank the speaker again.
Present your testing. You can go to present your testing.
Everyone, our next talk is going to be by Zhang Cheng from Shanghai Jiao Tong University. He's going to be telling us about compositional compiler verification.
Thank you. Thank you for the introduction. Hello, everyone. My name is Zhang Chen. Today, I will present our work, denotation-based compositional compiler verification. ComSearch is one of the most influential verified compilers. Its correctness proof is based on small-step semantics and simulation theory. Intuitively, simulation means that each target step is matched by 0 or more source steps producing the same event and reaching related states. This is powerful, but the proof structure is not always easy to reuse. Here is a small example. Suppose f and g are pure computations. They do not have I/O events, and they do not change the input variable x. If f is compiled to g, then in another context, the target program can compute y first and move print operations later. However, a simulation proof for fragment f to g is hard to reuse directly for the natural transformation s to t. The reason is that observable events, such as print, must be matched step by step in the simulation proof. If we look at simple textual denotational semantics, it is clearly compositional. Here, the semantics of a statement is defined as a binary relation between initial and final states. For some simple program transformations, their correctness can be defined by set inclusion. Then the correctness for sequential composition can be proved compositionally. However, programming languages such as C have much richer language features and more possible behaviors. Moreover, compilers often change the memory layout and the representation of program states. So such inclusion is no longer enough. We need more general refinement relations to relate source and target states. Traditional denotational approaches address parts of this problem. For example, power domain theory provides standard ways to model non-determinism and non-termination. They usually rely on a single global order on behaviors so that fixed points can be constructed to define the semantics of the recursion. But to keep the order simple, divergence is often handled in an absorbing way. In a partial calculus view, divergence is absorbed by terminating behaviors. In a total calculus view, divergence instead absorbs terminating behaviors. Neither treatment is suitable for compiler correctness, since divergent behavior must be preserved precisely together with its observable events. On the other hand, once we disallow this kind of absorption, it becomes hard to find a natural global order that handles all these language features. This leads to our key question. Once we consider all these features, can we keep denotational semantics precise with simple order structures while still having algebraic correctness proof? Our answer is yes. I will show. We begin with the semantics of statements. Consider a small language with non-deterministic choices and while loops. In this setting, the execution of a statement C may terminate normally, abort, or diverge. We describe its semantics using 3 separate behavior sets. The normal behavior is a binary relation between initial and final states. The error behavior is a set of initial states from which C may abort, and the divergent behavior is a set of initial states from which C may diverge. This idea is straightforward to formalize in ROC, where the semantic signature of a statement C is a record. This record consists of 1 relation for normal termination and 2 subsets of program states for error and divergence. So our first key insight is that we can describe the possible behaviors of a program using several simple sets. Then for each behavior set, we define an order or semantic operators to derive the semantics of program constructs. For instance, we formalize the behavior of sequential composition field by field. Normal termination is just relational composition. Errors and divergence are similar. For example, the sequential composition of C1 and C2 diverges if and only if C1 diverges or C1 terminates normally and then C2 diverges. We use the star operator and the infinity operator to derive the semantics of while loops. The star operator describes finitely many loop iterations, and the infinity operator describes infinitely many iterations of composition. Equivalently, normal termination is defined by taking a least fixed point, while divergence is defined by taking a greatest fixed point. In this way, we can build a simple order rings and then take fixed points separately for each behavior set. To capture observable events from statements such as print, we can naturally enrich each behavior set with an event trace. More importantly, we distinguish finite divergence and infinite divergence. For finite divergence, the execution generates finitely many events and then silently diverges. For infinite divergence, there are infinitely many observable events as the program diverges. If we extend the composition operator by concatenating traces, we can apply the same method to define the semantics of program statements. This extended composition also keeps the same good algebraic laws as the original one. To handle the classic stuttering problem, we use two additional simple operators to describe the divergence of while loops. I will leave the details to our paper. Next, we extend the idea to procedure calls. We start again from a textbook setting. A program is a list of procedures. Each procedure consists of an identifier as its name and a statement as its body. To keep things simple, call statements have no arguments and no return values. Following the program structure, the semantics is defined step by step, first for statements, then for procedures, and finally for whole programs. First, the semantics of a statement is parameterized by an oracle chi. The oracle chi gives the denotations of callee procedures that they may call. For the denotations of statements are previously introduced. The only new case is the call statement. Its semantics is defined directly by chi. Second, under the same oracle chi, the denotation of a single procedure or list procedures is a function that maps an identifier to a binary relation. For a single procedure, the binary relation is non-empty only when the input identifier is the same as the procedure's name. In that case, the binary relation is defined as the denotation of its body. For list procedures, the binary relation is defined as the union of the relations for each procedure in the list. Finally, the denotation of a whole program is defined by taking a least fixed point, which gives meaning to recursive calls between procedures. This is standard. Now we take error denotations and divergent denotations into account. So far, the oracle chi only describes normal termination, but how to capture errors and divergence from callee procedures? Our solution is to add a call behavior set. This set is a binary relation between initial states and queries at procedural call points. Here, a query records the identifier of the callee procedure and the state as a call point. For example, suppose a statement C may conditionally call F and then call G. Its call behavior set records all possible calls reachable from each initial states. As shown by the three legible arrows, when the if condition is true, C first calls F and then calls G. When the if condition is false, C directly calls G. The semantic signature of procedures has the corresponding fields. The difference is that a procedure starts from an incoming query. Similar to a textbook setting of procedural calls, the denotation of a single procedure is derived directly from its body. Finally, for a whole program P, the normal behavior is still defined by taking a least fixed point. Errors and divergence are then defined through a correlation. For example, divergence may come from local divergence or from an infinite chain of procedural calls. So we take the greatest fixed point of this semantic equation. This also explains why the call field is useful. The same idea extends to open modules. An open module is a module that may contain external calls. Its semantic definition is very similar to a previous definition for whole programs. The difference is that the the recursive equations for internal calls are solved by a fixed point, while external calls are left open, and their meanings are given by chi-O. We can apply the same method to define the semantic linking of two open modules. Intuitively, linking turns cross-module calls into internal calls. This gives us an equivalence theorem between semantic and syntactic linking. Here, the plus symbol denotes syntactic linking. It merges the procedural definitions of the two modules. We further found that this equivalence can be naturally reduced to the Beckett theorem. The diagram shows why this works for normal termination. Solving recursion inside M1 and M2 separately, and then solving their mutual recursion is equivalent to taking one joint fixed point after syntactic linking. Our second key insight is that this equivalence can also be extended to other behavior sets, such as error denotations and divergent denotations. The proof follows a simple algebraic pattern. Finally, let me turn to our proof method for compiler correctness. First, we consider simple transformations where the source and target use the same state representation. In this setting, transformation correctness can be defined by set inclusion. For deterministic but unsafe statement C, the target may have more normal behaviors. This is because once the source may go wrong, the compiler is allowed to produce any target behavior. For non-deterministic but safe statement C, the target may have fewer normal behaviors. This means that compilers may resolve non-deterministic choices in a particular way. But real program can be both non-deterministic and unsafe. In such more general cases, we describe transformation correctness as this. It means that every target normal behavior must either come from a source normal behavior or be justified by a source error behavior. For other behaviors, we define refinement in a similar way. This is where our separate behavior are useful. Normal termination errors and divergence can be compared precisely. Under this definition, the sequential compositionality follows directionally. Let me briefly walk through a proof. One typical proof goal is to show that every target normal behavior is either a source normal behavior or be justified by source error behavior. The first proof step follows directly from the refinement assumptions for C1 and C2. The second step follows from the distributive law of composition over set union. The final step follows from the commutative and associative laws of set union. The final step is directly from the definition of sequential composition. This is exactly the proof pattern we want to preserve, since such proof can often be automated in ROC. For commutator-style transformations, set inclusion is no longer enough for defining transformation correctness. We need more general refinement relations because the source and targets may use different state representation. So similar to a simulation machine in ComSearch, we define refinement between two denotations like this. For normal termination, this refinement condition says the following. Given a state matching relation R, for any related initial source and target state, every target normal behavior must either be matched by corresponding source normal behavior or be justified by source error behavior. The conditions for error and divergence are similar. To recover algebraic correctness proof, our key idea is to use the gamma function to reformulate each complex refinement as a simple set inclusion. Specifically, a gamma function takes source set behaviors and produces target set behaviors. Such a gamma is valid if and only if the reformulation has the same meaning as the original refinement condition. Our work shows that we can always find suitable gamma functions to reformulate each complex refinement as a simple set inclusion. More importantly, these gamma functions satisfy a common set of algebraic laws. With these laws, for example, the gamma normal is monotonic and preserves relational composition. This slide shows the general form of these algebraic laws. With these laws, even for ComSearch-style transformation, we can recover the same inclusion-based proof style we saw earlier. For example, consider the sequential compositionality again. A typical proof goal is to show that every target normal behavior is either a source normal behavior or be justified by source error behavior. The first step still follows from the refinement assumptions for C1 and C2. The second step is the key step. It follows from the composition-preserved law of gamma. The final step is still follows from the definition of sequential composition. With gamma, the same algebraic proof style also scales to other cases, such as horizontal compositionality for separate combination. To conclude, these ideas give a denotational framework for compositional and structured compiler verification. We have applied our approach to the computer front end and also to optimizations such as data code elimination and constant propagation for simple imperative languages. That concludes my talk. Thank you.
Time for one or two questions.
Thank you for the excellent talk. I can't pretend to understand all of it. There's quite a lot there. I look forward to diving deeper. So with the refinement aspects of things, is it modeled as subset relations? And then I have a comment just generally that subset relations being logical implication. When you have a diamond, then you have non-determinacy. And if you think of modeling refinements as conjunctive sequences instead, you might be able to recover determinacy and scale.
So this problem seems to relative to our refinement conditions. Is that right? I mean, the problem is about the simulation relation about our refinement conditions. Is that right? I mean, you can. Our approach is to use a gamma function to reformulate the refinement conditions, complex refinement conditions. So you can recover the algebraic proof style for simple set inclusion. Even for complex refinements, we can use inclusion-based proof style to prove the compiler correctness. So.
Excellent. Maybe we take it offline. That's
okay.
Let's thank the speaker again. And next, we will have Morel Leon from the Illinois Institute of Technology presenting to us about programming with responsive parallelism.
and Muller and my friend me, which I'm grateful for. What if we could write a web server that checks for denial of service attacks in the background, scientific simulations which gather new data while computing, and an LLM with continuous training, with fast parallel processing and I/O responsiveness in one elegant language. Let's show how this is not only possible, but more flexible than ever, and prove it by writing that web server. But first, let's see how fast their parallel processing and I/O responsiveness are usually achieved separately. Cooperative multithreading breaks down computation into smaller tasks spread out across multiple processors in parallel. Decades-long research has proven formal efficiency bounds to maximize throughput. Competitive multithreading, on the other hand, hides latency of I/O-bound tasks, time slicing on one or more processors, completing them concurrently, and it's competitive because it uses thread priorities, and the scheduler favors higher priority threads for high I/O responsiveness. Responsive parallelism is the combination of cooperative and competitive multithreading, and it has all of these benefits of both. To prevent a common bug that needs to be prevented for responsive parallelism is priority inversion, where a high priority thread waits for a low priority thread to finish. And primal is from a recent line of work, a key language for responsive parallelism that prevents priority inversions, and we'll see how. But first, let's see the primal commands. You can spawn a thread at any priority and sync on a thread. It blocks until the thread returns its value. A primal thread is simply a sequence of commands. Let's see this priority inversion. We have a high priority thread, which is waiting for TD, a low priority thread, and it's not finished yet because we have many medium priority threads that are taking up all of our processor time. So we have a priority inversion. We want our high priority thread to only depend on work in parallel that's at a higher or competing priority. Primal currently uses its type system to statically rule out priority inversions. We have this sync rule, simplified for clarity. We have that the priority of the thread we sync on upper bounds the priority of our current thread. So primal threads are safe from priority inversions. Primal combines cooperative and competitive multithreading into responsive parallelism, and it has all the benefits of both. Almost. Right now, primal is limited and inflexible, and we'll see why. Competitive threading systems usually use integer priorities, and we expect to be able to calculate on them and bind them to variables since they're first class. Here we want to increment the current priority, but priorities are not first class in primal yet. If we return to our web server, our classification loop runs in the background, classifying clients as malicious. And in the foreground, we have our accept loop, which accepts new clients in the foreground. And we want to be able to handle a denial of service attack by changing our priority of our classification thread to a higher priority so that we can pay attention to malicious hosts until the threat is gone, and then we return to a low priority. But changing priority is not possible in primal. So we extend primal to solve these limitations, making priorities first class and adding dynamic priorities so that a thread can change its priority using our new change command. So let's redesign Primal's type system for dynamic and first class priorities, which introduce endless possibilities. There are multiple priorities that the thread runs at, and a priority expression can evaluate to one of many possible priorities only known at runtime. But why are so many possibilities a problem? We might run into priority inversions. And so we need to modify the sync rule to rule out priority inversions. Currently, we only have single priorities, and so we can't account for all of the possibilities that we have with dynamic and first-class priorities. To solve this, we use refinement types, which give us all of the constraints that we need. A refinement psi can represent the multiple priorities a thread can run at. Here we have a thread with 3 priorities, and a refinement can represent the possible priority values that an expression becomes at runtime. Here, this will be high or low, and its refinement has both of those priorities. A refinement limits a priority possibility using a construction of constraints. For example, if we have a priority P such that 2 is less than or equal to P and P is less than or equal to 5, we have the priorities between 2 and 5, and we use set notation as an abbreviation for clarity. So, right now, our sync rule has that the priority of the thread we sync on is an upper bound for our current thread's priority, but we want to use refinements to represent all of the different possibilities. So, how do we do this? Refinements upper bound the many possibilities of those 2 different possibilities using this refinement judgment where the possible priorities of the thread synced on is an upper bound for the current thread's possible priority value. And this is defined as all of the priorities in the first refinement must be less than or equal to all the priorities in the second. So before we had first-class priorities, priorities had no type, but now we can use a refinement to type all of the possible values it has at runtime, and do the same thing with threads, replacing the single priority in the old thread type with all of the possibilities in this refinement that it can run at and change to. We also need to update Primal's command type because, as I said before, a Primal thread is a sequence of commands. But this is not as simple as replacing a single priority with a refinement. I'll show you with this example. We have thread B taking on priorities 10 and 11. We know its type here, it's an int thread. And thread A increments its priority and syncs on B. We have that the sync command is only allowed to start at priority less than or equal to 10 in order to prevent a priority inversion when syncing on B. And the change command changes the priority so it has 2 priorities in its duration and it ends at a new priority. So we need 3 refinements to type a command: the start, duration, and end refinements. our new command type has these 3 refinements in it, and this is what we need to rewrite our sync rule. Our new sync rule has this new bound premise where we have that the starting priority is, okay, so we have that the priority of the possible priorities of the thread that we sync on is upper bounded by is an upper bound for our start priority of the current thread. And all 3 of these refinements are the same because when we sync, we don't change our priority. So now that we know how to, now that we can show that our threads depend only on higher and competing work in parallel, we can type a thread. Here we have thread C trying to sync on thread D, which takes on priorities 4 and 5. First, it changes its priority to either 3 or 5. And so we get all of the start, duration, and end refinements for each of these commands. And in the interest of time, I won't go through each one of them, but when we sync, we're definitely at one of the priorities, 3 or 5, and we have to check with the sync rule if we have a priority inversion to check if the priorities 3 and 5 are upper bounded by D's priorities 4 and 5. But this violates the sync rule, and so we have a priority inversion. So let us fix this bug by adding a change command and change to priority 4. And now when we sync on thread D, we check if the priority 4 is less than or equal to the priorities 4 and 5, and it is, so we have the upper bound that we need, and we can give thread C its type. First, we need to know what priorities thread C takes on in its whole duration. To do that, we take the union of all of the durations of the commands, which is our intuitive strategy. Formally, we use composition and subtyping, but we know that this thread C takes on priorities 1 to 5, because it starts at 1, and it changes to priority 3 or 5. And so we can find the type for this thread, which returns an integer. So it is an int thread with priorities 1 to 5. Now, how do we bound the response time of our threads? Well, we just redesigned Primal's type system, and our program can now become a well-typed program. And we need to prove that this well-typed program gives us our efficient response time. To do this, we have a cost semantics that turns programs into directed acyclic graphs. And we restrict these graphs to be well-formed, which is a key property we prove means the graph has no priority inversions. And we use our cost semantics to turn our well-typed program into a well-formed graph. And we prove that with a well-formed graph, we will be able to bound our response time efficiently. And the entire proof you can see in the paper. Now let's see Primal's new implementation with type inference for dynamic and first-class priorities, which is inspired by liquid types. And we have a new backend which compiles Primal to multi-core OCaml. And finally, we return to our web server again. Here, our web server changes its priority depending on how many connections we have, which is how heavily loaded the system is. It also calls process hosts because the classification needs to know which hosts are bad hosts that may be overloading the system. When we first wrote our program, it had this error. Sorry. Am I over time? Okay. Okay. We fixed this bug using dynamic and first-class priorities, and Primal is now flexible and has a proven efficient response time.
Thank you so much for the talk. In the interest of time, we have to move on to the last speaker, who is going to be Sonling Jia from Purdue University, who is going to tell us about how to program better with reachability types.
Okay, hi everyone. I'm Sonling Jia from Purdue University, and today I'm going to talk about my work, Escape with Yourself, Sound and Expressive Bidirectional Typing with Avoidance for Reachability Types. So this is a very long title, so where do we start? We start with the last two words. What are reachability types? So basically, this kind of a type system where we want to reason about resources via variable names. Our goal is that we track the sharing of resources instead of restricting the sharing. And the goal is that we want to achieve better expressiveness in comparison to, for example, the statically safe fragment of Rust, which strictly enforces the shared XOR mutable principle. So for example, here in this counter function, we see that there are two closures, incur and deter. They act as methods. They too share the underlying mutable ref cell named C. So for all three of them, we annotate C in the type qualifier of their types. So that's what sharing is tracked in those cases, in functional impure cases. But then when incur and deter are returned out of this counter function, they escape. So we need to preserve tracking on such escaping data. So when the return pair is assigned to the new variable name called counter, we need to annotate the extracted incur and deter with a new type qualifier using the name of counter. And after we have tracking in places, it's time to make some profit and do some real reasoning. So here, in an on-demand manner, functions, each of them, they can choose to request disjoint parameters. When they choose to do so, they annotate that tiny little diamond symbol on the type as a type qualifier of their parameters. So each of them represents that the parameters there should be disjoint from one another. So in this way, a function combinator like parallel can request that their parameter sums are separate from one another. So this gives us static safety in terms of no data racing. So all these reachability typing stuff have been declaratively established in prior works. So in this work, what we want to do is that we want to build type checking algorithms in a sound and expressive manner towards such reachability types. So what are the challenges? Well, since in our approach, since in the design of the type system, variable names is so important, naturally, and we will know that when you are actually programming, names are not enough to track data. So there are two really important cases where we observe that names are not enough to preserve the tracking. First of all, there's the avoidance issue where, for example, in an inner strobe, we define a variable x, and the data we're returning from this inner strobe is also should be qualified by this x. But then in the outer strobe, since all names are ill-strobed, that name has to be avoided from the typing. That's the first case. And the second case is about polymorphism. For example, for an identity function where the parameter reachability is polymorphic, represented by that diamond symbol as well. And the result qualifier has to depend on the bound variable of z. But the bound variable cannot appear in the result of the application and need replacing. So in the first part of this talk, we'll be focusing on the first challenge of avoidance. And before I go on, I should note that avoidance is not a problem that is unique to reachability types. It is commonly seen in any kind of dependently typed system without evaluation types. There are several examples of them. For example, there's bounded existential types, there's dependent object types, which is a foundational calculus of Scala, and also it's commonly seen in ML module. And this is an example extracted from some paper actually discussing ML module and signature avoidance. So in the really simple case, how do we do avoidance? Well, the idea is that, for example, if a variable y needs to reach x, and x went out of scope, and x is reaching some nameless resources, then we can just bypass x and replace the ill-scoped variable x with the upstream reachability, the diamond symbol, outright, so that y is now the new name for this distinct, unnamed resource, which is good. But would this same replacement mechanism work on more intricate cases, for example, on escaping data types? Actually, no. So since the diamond symbol needs to mark distinct resources, for example, here in this example, we have a pair, and both components of this pair is referring to the same variable x. If we just do a naive replacement, replacing all occurrences of x with diamond symbols, then basically this type will be changed into the wrong meaning, meaning that both components are referring to distinct components. So this is not what we want. Then what can we do about them? Well, the correct way is designated in reachability types to do so is that we need to go through an indirection via something called self-references. So you may think of these self-references, named P here, as something similar to these pointers found in object-oriented programming. So this notion of P represents the whole pair. So instead of saying that both components are reaching some external variables, we say both components reach some resources that is enclosed within this pair itself, and this pair itself is reaching the unique diamond resources. So in this way, we preserve the invariant of those both components sharing the same data. So here comes our title. The core mechanism is that we track escaping data with self-references. That's the title pun is escaping with yourself. Okay. And yeah, in this signature of the pair type, P represents the whole enclosing pair over approximating components. But in prior work, actually, pairs with self-references and pairs without self-references, there are incompatible types. So before and after escaping, the types actually change. So this has two undesirable results. First is that we need to do some term level coercion for escaping. So specifically in this example, you can see that we need to do some eta expanding, basically extracting components from an existing pair and reconstruct it using a different type signature. That's the first undesirable thing. And the second is that since the type signature is different, we need to use different specialized eliminators, basically component extractor functions before and after escaping. So this is really undesirable. So in this work, in order to fix such problems, we use some combined development on both the declarative side and the algorithmic side. We start with the top-level algorithm, we need to do some kind of polarity-based avoidance that in some of the covariant cases, we replace variables with self-references, and in contravariant cases, we need to remove such ill occurrences of variables. And to prove such variable is actually a good way to do this, a sound way to do this, we need to have a spec. And this spec, for this spec, we develop type and qualifier subtyping, which is precisely what's missing from our prior work. And why didn't our prior work have such subtyping? Well, for some reasons. First of all, self-references in subtyping, they carry different semantics on both sides of the subtyping because they denote to the outer qualifier respectively, and the outer qualifier can change in subtyping. So their semantics will also have to change, and that change will have to be covariantly. Secondly, while the covariant semantics of self-reference allows us to have self-references safely occurring in all covariant positions, for some of the use cases, especially when we were dealing with church-encoded data type structures, we still need the self-references to occur in certain of the contravariant positions. So in this work, we have some syntactic restriction to allow such negative occurrences in where covariance or contravariance doesn't really matter. You will find more details in our paper about this. The second challenge of our algorithmic design is about polymorphism. And yeah, so basically we need to find a qualifier to replace the bound variable when we are considering reachability polymorphism. So our solution here is that we develop a bidirectional typing algorithm that infers qualifiers from parameters. For bidirectional typing, we know, so that basically means that we need to have two modes. One mode is that we infer the types and qualifiers, and one mode is that we check the types and qualifiers. But for this work, for this specific goal, we need more. So the first newly added case is that we need a hybrid mode that checks the type but infers a qualifier. You can see this from the first example shown there. So we need to, when we are considering applying the identity function with a new variable x, we need to infer the parameter qualifier x on x by checking its type and infer the qualifier x, and then using that inferred qualifier for substitution. So this kind of polymorphism is what we call a lightweight polymorphism as an alternative to explicit quantification and instantiations. And to backing up this hybrid case that's checking the type and infers a qualifier, we also introduce a new algorithmic subtyping form that infers a super qualifier while checks the upper bound of the type. What's complicated about it is that the interesting cases can again be found on self-references. For example, in certain types of function applications, we will be coercing a type without self-references into a type with self-references. So by such a subtyping, we will be posing constraints on the self-reference of P. So more details can be found in our paper about how we define our unification for qualifiers, which is also inspired by the either instantiation approach for type polymorphism. So a quick recap, a quick sum up. Our development is fully mechanized in Link 4, the proof assistant. Our mechanism is split in roughly two parts. The first part is about the declarative specification. We have combined type and qualifier subtyping, and we prove semantic type soundness about it. And for the algorithmic implementation, we build qualifier checking and inference algorithms. And on top of that, we also have algorithmic avoidance conversions carried out in an implicit way. And we prove soundness and decidability of our algorithm, that our algorithm designs terms in finitely many steps, and all accepted terms are valid with respect to our specification. For evaluation examples, we did several of them. First, they include church encodings of data structures and also primitive forms of pairs and lists. Also, we try to explore patterns of race-free parallelism and the safe use of capabilities, for example, scoped file programming. And also, we explore different kinds of reachability patterns, including escaping data structures, and also, for example, structures with separate components. For example, this M-list stuff, classic example you will see with separation logic, basically. So as for annotation burden, in most cases, we see that on these examples, qualifiers at less than 20% of the size, and these numbers should be even lower on larger examples. And also in terms of the performance of a type checking, the timings of our type checking algorithm on different examples fits a quadratic curve and scales expectedly. So before closing up, I want to recap a little bit about the landscape of research on reachability types. So the initial language design was proposed in 2021, and later on in 2024, polymorphism and freshness marker has been proposed to strengthen the language. The language has been leveraged to do effect reasoning. So there was a GraphIR compiler defined, there are equational series explored, and on Wednesday there was a talk that was also given by me on how to use that to do type state programming. And also there's parallel work on how to strengthen the store topological, for example, how to allow cycles to be expressed in stores. There's also one talk on Wednesday. But the emphasis of this work is that we want to build algorithms and implementations, and we want those algorithms and implementations to be sound and expressive enough for escaping data types, and those can provide guides to prototype designs. So to conclude, in this work, we are looking at expressive algorithmic reachability types. By expressiveness, there are several things we are looking at. First, we want to track resources in escaping data. Second, we want to automatically avoid ill-scoped variables from types. And thirdly, we want to support inference for reachability polymorphism. So in all of these cases, we can see that the concept of self-references is both a key mechanism and the main challenge. So our development goes into two folds: the declarative specification with subtyping that is expressive enough for conversions with respect to self-references, and we prove type soundness by logical relations. And for the algorithmic part, we devise checking and inference algorithms, we devise implicit avoidance conversions, and we extended the bidirectional typing mode to fit into the picture, basically. And our solutions proving sound and decidable, fully mechanized in Link 4, and our artifact is available online. Thank you very much for coming, and I'm happy to take any questions.
Time for questions. So I would like to ask a little bit about the evaluation of annotation.
Yeah.
Right. I mean, not all annotations are necessarily equally difficult to write. Are there certain ones that you think developers might find more burdensome than others?
Yeah, good question. So first of all, I should explain a little bit about how that percentage number calculated. So that's, you should think of it like number of tokens, like words we wrote. And for example, for a reachability annotation, sometimes it contains multiple variable names, so individually it contains different tokens. So that's how we calculated it. In that regard, I think 20% is not a great number. Secondly, I think definitely, as you hinted, there are some of the annotations that should be harder to figure out than some other annotations. I think this is especially true when we are considering higher order functions, because when higher order functions, we need to consider that which level is this resource being captured, and sometimes when we are taking in higher order functions as arguments, this is more a problem because we have to speculate what kind of functions we are receiving. So that would be the challenging case.
Questions from the audience?
Nice talk. I think this is works about the type algorithm, right?
Yeah.
So I'm curious that what is the I guess it's a type is probably need to have some approximation, and otherwise it's probably hard for user to use it. Otherwise, user need to write on very precise type. So is there the loss of user burden, or what happens if the user provide a not quite precise type? What happens?
Yeah, as with all type systems, the programs getting rejected, the user see a type error. They can have the chance of fixing that. Of course, I guess that I believe that's the nature of doing typed programming.
Is there any hints to the user which part is wrong?
Yeah, definitely. So basically, you can think of function applications as chats of coming in two forms, subsumption chats and the separation chats. For both of the cases, we will be providing you, hey, there's one argument with a concrete variable name, which I think is true, that is appearing on the actual side, but not allowed on the expected side.
Okay, thank you.
Thank you.
Let's thank the speaker again. And thank you to all of the speakers of this session, along with our AV team, and to all of the attendees. Thank you.
presentation. My name is George Zikilic. I'm an assistant professor at Singapore Management University, and I will chair this session. So we have 5 talks in this session. Each talk is supposed to be 17 minutes plus 3 minutes for questions. To speakers, I'll give you a sign when it's 15 minutes, so when you have 2 more minutes. And with that, we can start. So the first talk of the session will be given by Jingbo Wang, who will tell us about probabilistic inference for data log with correlated inputs. The floor is yours.
Okay, thanks, George. Okay, so let's take a quick refresher on data log programs. It typically has multiple parts. So the input facts are typically representing the known facts. Here, you can use that to represent the edges of a graph. And then the rules specifies like how a fact can be derived. In the end, you have the queries. So this example is for a very simple graph reachability problem. And then you provide those 3 informations to a regular data log solver like Silfly. And then in the end, the solver can answer questions like whether the output fact pass17 is true or false. So these are basically like a general intro of data log program. So why do we care about data log? Data log has been widely used in a lot of applications, like information flow analysis, data risk analysis, or database migration, data transformation, or knowledge graph representations. So those are good. Data log is pretty powerful in a lot of applications. But then, in a lot of times, real-world scenarios often involve with uncertainty. So this requires us to combine logical programming with probabilistic inference together. Here is another program which is adapted from the one you saw from the first slide. We can associate each input fact and the rules with a corresponding probability. This kind of program can be handled by a lot of previous solvers working on probabilistic data log, or like a prolog. And then these solvers are trying to answer a different question, which is about the probability of pass17. These are pretty good, and we can actually use this solver to resolve probabilistic data log program. But the problem is all those prior works assume that the inputs are independent. But actually, in a lot of times, the real input fact can be correlated. So let's take a look at one example. When the cardiologist is trying to diagnose some heart-related disease, they may have 3 input facts there to use to do certain kind of inference. And then for 2 of them, like chest pain and abnormal ECG, those 2 facts may not be independent. They are actually correlated from the literature. And then there could be another case for using data log for set channel analysis. You might have see 2 facts here. One for encoding program statements like XOR operation. This one simply means like V1 equals to V2 XOR V3. And then you have a share relation saying that these 2 variables are sharing the same register. So those kind of information are actually also correlated. The reason is because the source operand V2 and the target operand V1 are highly likely to be placed in the same register according to the register allocation in the compiler's backend. So then, given all those kind of cases, if we provide such kind of programs to the existing probabilistic data log solvers, they would produce unsound results because they mistakenly assume independence. So this is what we are trying to resolve here. We are trying to propose a probabilistic variant of data log that can deal with arbitrary correlations among input facts. And the problem is removing such independence assumption would introduce a lot of challenges. The first challenge is that it would make the probability computation much more complicated. In the earlier case, in all the previous works, when they enforced independence assumption, all the joint probabilities can directly be computed by simply multiplying them together. However, when we are removing those kind of independence, this equation is no longer there. So for instance, given the same example program, those three facts are correlated. So we can no longer simply multiply their probability together to compute their joint. The other problem is that it's typically hard for users to provide the full joint distribution table, especially when you are going to use that for some program analysis tasks. Some of the cases, we would have a very large set of input facts. For instance, in this case, we have 3. And in order to provide a full joint distribution table, you need to provide an exponentially large table. And in many of the cases, it would be too hard and too user unfriendly. So user might only just give us one or some of the partial conditional probabilities they have in mind. And with this kind of partial information, we only have a few marginal and conditional probabilities. In such a case, when we are computing the probability of a query, the ground truth answer we can have is actually an interval instead of a single value. This is not because our solver is imprecise. This is mainly due to the partial knowledge provided by the users. So here, let's take a closer look of our problem definition. So in the left side, there is a Prolin program. Similar to Problog, we would specify input probabilities. And then we will also specify correlations. So user can declare arbitrary correlations among input facts using the format of conditional probabilities. And then user can also specify rules, similar to the classic probabilistic data log solver. Eventually, you want to query the facts and the probabilities. Given such a program, our objective is to actually compute the probability of the query, which is actually a bound. And then we want this bound to be not only sound, but also tight. So soundness here means that any actual true probability should always be encapsulated inside this bound. And to resolve this, we actually provide 2 methods. The first one is the exact inference, which is working on computing the ground truth probability bounds. And then we also have the approximate inference for a scalable delta exact inference. So you might not know what delta exact is, but don't worry, I will explain that in a few slides later. So let's first take a look at the exact inference. In a high level, we reduce this exact inference to a constraint optimization problem. So the constraints here are mainly used for encoding the correlations and derivation structures specified in the original input data log program. And then we also have the objective, which is an expression associated with the query. So in the end, you might want to minimize your objective to get lower bound and maximize your objective to get upper bound. So this is pretty straightforward, and then it works well for small cases. However, theoretically, this one is sharply hard, and in practice, it cannot scale to the larger instances. Mainly because of 2 reasons. The constraints may get larger, and also the optimization objective is nonlinear. In order to make the whole thing scale to a much larger cases in practice, we actually produce another approximate inference, which has 2 requirements. We want it to scale to the realistic instances. For instance, there are a lot of very, very large scale program analysis tasks encoded in probabilistic data log. They may cover like hundreds of thousands of facts. So we want our approximate inference to achieve this kind of scalability. And then we also want it to give precise bounds. So how do we define precision here? It's called delta exact. So it simply means that the bound we computed, L and U, is within delta distance of the ground truth interval L star and U star. So here is a close look of our delta exact algorithm. our first step is trying to infer correlation types for a pair of facts. And then given such type, we can do the approximate bound computation. In the end, we would gradually refine the bound until they satisfy the delta exact precision. So let's start with step 1, correlation type inference. So this step is mainly trying to infer the correlation between a pair of facts through a very cheaper inference. So two facts can be positively correlated, negatively correlated, independent, or unknown. So here we don't really need the exact value of this correlation. Only the sign or polarity of the correlation would buy us enough benefits for generating a tighter bonds. So for the correlation between input facts, we would resolve that through constraint solving. For the derived facts, like outputs, we would conduct some static analysis over the derivation graph to address of them. So as for these two mechanisms, they are not disjoint, they are actually working together. So constraint solving first tries to infer more and more correlations between inputs, and then those information are propagated to the static analysis to infer more correlation types. So if the static analysis fails to infer anything new, and then it would safely fall back to unknown type and delegate this to constraint solving sometimes. So this correlation type inference works very hard on generating correlation types, and then this information is provided to the approximate bound computation to get some actual numerical bounds for the probability of the queries. So our second step is basically built on a known technique called Flatirons inequalities. It is used to combine probabilities together. For instance, if you have two expressions with their lower bound, upper bound, and then you want to compute the probability of their conjunction or disjunction, you can apply these simple rules to do that. So this is pretty straightforward. However, it's not tight, and in actual cases, it's pretty loose. So let's take a very concrete example. If I replace those symbolic values with concrete numbers, then I'm gonna compute my bound for the conjunction of the events, which is pretty loose. However, if I happen to know the correlation type information between E1 and E2, I can actually compute a tighter bound by refining my conjunction rules. So then I can get a roughly tighter bound to compute the conjunction of these two events. So to wrap up for the step 2, it is actually utilizing the correlation type computed from step 1 to potentially generate a tighter bound. Okay, so this bound we are generated is guaranteed to be sound, but there is still no precision guarantees. Remember that we want our bound to be delta exact, which means the bound should be within delta distance from the ground truth. So then this inspires us to develop the third step, which is to iteratively refine the bound until they are within delta distance of the ground truth. So let's start with the step 3. We first take a look at the line here. There are two dots here representing the bound we computed from step 2. And then there are also like L star and U star representing the ground truth interval, but they are unknown. We don't know them. We don't know where they are, but we only know like they are inside the L and U. So this region marked by the ground truth is actually a set region. This simply means that this region is jointly satisfiable with the constraints phi. Phi is generated from the exact inference. And then any interval that is intersecting with this green region would be set. And then the remaining region are actually unset. So if you happen to have an interval that is disjoint from the green region, would also be unset. Okay, so let's start from the interval we computed from step 2. We want to gradually increase the lower bound and decrease the upper bound until at some point it is within the delta distance from the ground truth intervals. So here, we first start with a lower bound. Here we introduce a notion called the bound of lower bound. You might see the bound for lower bound is actually L and L1. And then we gradually increase this bound of lower bound. It would eventually turn from unset to set. And then we would temporarily stop here. In the same time, we would apply the same strategy to the upper bound. We would also maintain a bound of upper bound. So this bound would gradually decrease until at some point it also finishes the transition from unset to set. So with this bound of lower bound and the bound of upper bound, we are gonna do some binary search to further tighten these two bounds. Eventually, we terminate if the length of bound is within delta. So then the final L minus and U plus would be the sound and delta exact bound we are gonna deliver to users. So let's put everything together. We start from the LU computed by the step 2. And then by doing the iterative refinement, we are gonna compute the final bound L minus and U plus. They are guaranteed to be within delta distance of the ground truth bound. Okay, so here is our implementation. We instrument SILFLY for data log solving, Groovy for optimization, and CBC5 for constraint solving. There are two kinds of benchmarks. One set is from discrete Bayesian networks. The other one is from large-scale set-channel program analysis for cryptographic algorithms. So there are two takeaways we wanted to highlight for tightness and scalability. For scalability, we actually compared the exact inference and our approximate inference. So the exact inference can only solve 40% of the benchmark. In fact, a large portion of set-channel analysis, they cannot be solved by the exact inference, while the approximate one can solve all the benchmarks. And for 76% of the benchmarks can finish under 100 seconds. As for the tightness, for the benchmark where the exact inference can finish, we can actually compute the precise bound error. So for those ones, we computed the error, which is 0.1% in average. So to summarize those, the approximate inference we proposed is quite scalable and tight in practice. So to sum up, data log input facts can be correlated in practice. And if we ignore that, it may produce wrong answers. So our work is trying to resolve this problem by proposing the first probabilistic data log framework to support arbitrary input correlations. And we propose both exact and approximate inference. And also we put the QR code for the tool here, so please try it for application. Thank you.
All right, any questions?
Hello. Yeah, nice talk. I'm Shaurya from UIUC. My doubt is that your procedure where you are using the SAT solver and then the binary search thing, I could in principle use that without the first two steps and starting from 0, 1, right?
You mean we cannot start that from what reason?
Yeah, 0, like they are just probabilities. You compute this L and U bounds and then try to refine it. I can also in principle start from L being 0 and U being 1, right? Because all these are probabilities.
Yes,
so that
but if you start from 0 and 1, that might involve more set solver invocations because you are starting from a looser bound, right?
Yeah, so that's what I wanted to ask. Did you do that ablation and was it giving a lot of, because your bounds are 0.3, 0.8.
Yeah, we have that. We have that result actually. So if you, so basically you are saying we do some ablation study to remove the correlation type inference, right?
Yeah, exactly. So that was there because it was giving you a lot of benefit, or is just some optimization to get the result faster?
It actually would like increase your runtime for getting the bounds. So that's yeah, that's in our ablation study. Okay. We did do that. We indeed do that by throwing away some of the components like step 2 and 3.
Makes sense. Okay. Thank you. Yeah.
Thank you for the nice talk. I was wondering about whether you support the full data log or there's a certain fragment, and if you were to do, say, negation or complementation, how that would affect the efficiency of the runtime.
Okay, so we indeed support a negation, but we restrict the negation should be stratified in our probabilistic data log program. And also the negation have a different semantic interpretations in the probabilistic sense as compared to its deterministic semantics.
I see. Do you compare with, say, lobster or scallop or other kind of probabilistic?
Actually, yeah, scallop, the problem is that scallop, they similar to problog. So scallop was originally built from problog. And then they all enforce the same assumption that the input facts are independent. So the value they computed is a single value, which is different from the assumption we are having from the program we are trying to solve.
I see. Thank you.
Maybe the next speaker can set up and we can take one more question. Yep.
Thank you for the great talk. I wonder if there is a asymptotic complexity for the approximate inference.
Yeah, so even though we didn't do that theoretically, so we do that empirically to kind of try to describe the runtime complexities with the size of program gets increased. So from the empirical results we have, the plot is nearly polynomial. So we think it's quite efficient and it's not really solving the sharp p-hard problems.
All right. Let's thank Jimbo again. So the next talk will be given by Satoshi Kura, who will tell us about the hierarchy of supermartingales for omega regular verification.
All right. Thank you for the introduction. Right. So in this talk, we consider the verification of omega regular properties of probabilistic programs. So concretely, suppose that we are given Markov chain together with an omega regular specification over its traces. So here, the Markov chain represents a probabilistic program. So its state space may be infinite in general. And moreover, we consider a specification expressed as either a street or parity condition. And our goal is to determine whether the Markov chain satisfies the omega regular specification with probability 1. So here's an example. So this program repeatedly runs a biased random walk while incrementing the initial position. And in this setting, one question we may ask is whether the location L1 is visited finitely often with probability 1. Another question is whether L0 is visited infinitely often with probability 1. These are typical examples of qualitative omega regular verification problem. And in general, omega regular specifications are expressed using street conditions, which are finite conjunctions of street pairs. Since a finite conjunction of street pairs can be handled component-wise, we focus on a single street pair without loss of generality. And formally, a street pair for a Markov chain is defined as a pair of subsets of its state space. And a run of the Markov chain satisfies the street condition if either A is visited finitely often or B is visited infinitely often. And there's an existing work on this problem. Street supermartingales are an existing technique for verifying omega regular properties. And they can be viewed as a generalization of ranking supermartingales where the ranking condition is adapted to a street pair. So formally, a street supermartingale is defined as a non-negative function that satisfies these three conditions. So if the current position belongs to A, then the expected value of R in the next step decreases by at least 1. If the current position is in B, then R may increase in expectation, but by at most M, where M is a fixed constant. And if X does not belong neither A nor B, then R must be non-increasing in expectation. So this is the definition of straight supermartingales. And the existence of a straight supermartingale guarantees almost sure satisfaction of the straight condition. Intuitively, if the straight condition were violated, then states in A would continue to occur, but states in B eventually disappears. So by the ranking condition, the value of straight supermartingale continues to decrease, and which eventually violates the non-negativity condition. So this is the intuition of the soundness. So now, let's consider how powerful are straight supermartingales. Unfortunately, straight supermartingales cannot verify the simple example shown here. In this program, this program is a simplified version of the various repeated random walk that I showed earlier. But here, the current position M is deterministically decremented. And in this case, the straight condition is satisfied almost surely, but there's no straight supermartingale. Intuitively, this is because in this case, we cannot satisfy both the ranking condition and non-negativity condition as shown in this picture. So to give more powerful proof techniques, we introduced several new supermartingales for omega regular verification. And also, we study the relationship between these new notions and the existing one. And also, we show some completeness results for our new supermartingales. And then, we implement automated synthesis algorithms, and evaluated the advantages of our new supermartingales. Okay, so this slide summarizes the hierarchy of the different notions of supermartingales, and in the middle column, this is the hierarchy for supermartingales for straight conditions. The bottom one is the existing one, and the other three are new notions. And these four notions are ordered in this way, and each inclusion relation is strict. And among these notions, generalized straight supermartingales are complete for positive recurrent problems, and distribution varied straight supermartingales are complete for null recurrent problems. And also, we additionally introduce supermartingales for parity conditions, which is shown on the right-hand side. Okay, so from now, I'm going to introduce these notions. So let me first introduce the notion of generalized straight supermartingales, or GSSM. The definition of GSSM is almost identical to straight supermartingales, but we dropped the condition for B. And so this relaxes the definition of street supermartingate. But despite this relaxation, GSSM remains sound, and its existence guarantees almost sheer satisfaction of street condition. And moreover, GSSMs are strictly more powerful than street supermartingets. This is because, they can verify the counterexample for street supermartingets that I showed earlier. Because we relaxed the condition for, we relaxed the ranking condition. Next, I will explain the competence result for a generalized street supermartingate. So, given a street pair, we call a Markov chain a positive recurrent if the expected number of A steps until reaching B is finite. And also, we call a Markov chain a null recurrent if the number of A steps until reaching B is finite almost surely. So the relationship between a null recurrence and a positive recurrence is analogous to the relationship between almost sure termination and positive almost sure termination. And we showed that GSSMs are complete for positive recurrence. This is a consequence of the fact that, this is a consequence of the least fixed point characterization of the expected number of steps. But I'm not going into details here. Okay, next, I will explain how we can go beyond a positive recurrence. So I'm going to introduce two notions of supermartingate. Here, we borrow ideas from verification of almost sure termination. So in this setting, a more powerful supermartingate can be obtained by replacing the code domain of a ranking supermartingate. For example, there's a notion of a lexicographic ranking supermartingate, and a lexicographic ranking supermartingate use the lexicographic order on tuples of non-negative reals. And similarly, distribution varied ranking supermartingates use the stochastic order on distributions over natural numbers. And this extension makes it possible to go beyond positive almost sure termination. So we use the same idea to omega regular verification. We define a lexicographic generalized straight supermartingale using lexicographic orders, and we define a distribution valued straight supermartingale using the stochastic order. The formal definition of LexGSSM is almost the same as that of GSSM. But here, we use the strict and non-strict lexicographic orders in the ranking condition. That's the main difference. And similarly, we define a DVSSM using the stochastic order in the ranking condition. Then we can show that these two notions are also sound for omega regular verification. And moreover, we showed that DVSSMs are also complete for null recurrence. So this implies that DVSSMs are the most powerful super martingale in our hierarchy. But however, they have a drawback, which is, at present, we do not have an automated synthesis algorithm for DVSSMs. And in our paper, we also present examples that separate 3 different classes of super martingales. So this implies that the inclusion relation between these notions are strict. But I'm not going to explain details. So okay. Next, I will explain super martingales for parity conditions just briefly. So, it is known that parity conditions are equivalent to state conditions, and also, in the case of non-deterministic systems, progress measures are a standard technique for proving, verifying parity conditions. So we combine the ideas of progress measures with Markov chains and obtained a new kind of super martingales shown here. And we do not explain formal definition, but we showed that LexPM-SMs are as powerful as LexGSSMs. This is proved by constructing mutual translations. And this mutual translation suggests that LexPM-SMs are not just as powerful, but also practically has advantage because LexPM-SMs often give a smaller certificate. Right. Okay. Finally, I briefly explain our implementation and experiments. So our implementation is based on a template-based synthesis. So we assume that program variables are real valued, and use a polynomial template for super martingales. Then we generate a constraint and solve them to synthesize a super martingale. For lexicographic super martingales, we additionally extend an existing algorithm to automatically determine the number of lexicographic components. And this is the experimental result. So this result shows that, so these results are consistent with the theoretical hierarchy. And also we can see that LexPM-SMs are in practice performs better than LexGSSMs. Okay, so that's it for my talk. Last comment, sorry. So our implementation is available online. So if you scan this code, you can find it. Okay, that's it. Thank you for your attention.
Any questions? All right, I have a few. Excellent work. I really liked your talk.
Thank
you. So I have a question about, so for probability one reachability in lexicographic ranking super martingales, there are works that considered relaxing the non-negativity conditions of some components.
Yes.
Have you considered this for LexGSSMs?
I think the answer is I haven't yet, but I think that's an interesting direction for future work. Yeah.
Okay, I have one more question. So in your completeness guarantees for positive recurrence and null recurrence, do you also assume the supporting invariant, which basically captures reachable states? Is this assumed to be a part of the certificate, or?
we don't explicitly handle invariant in our theorem, but it's relatively simple to combine invariant in our framework, and so roughly speaking.
So maybe to clarify my questions, I mean, for completeness guarantees, for the certificate to be complete, I mean, the defining conditions usually need to be restricted only to reachable states. So are you assuming that basically you have the set of reachable states or some sort of invariant which captures it?
Maybe there's some so completeness. So well. So in our problem setting, we consider actually I didn't explain very explicitly, but our problem is to show that omega Regel specification. So show that the Markov chain satisfies omega Regel specification for any initial position. So.
Oh, I see. I see. Have you then considered a variant when you're given an initial set? Would something change? I guess soundness will still hold, but what about completeness?
I'm not sure. What would be the statement for competence in that case?
Okay, maybe we can discuss offline.
Maybe you can talk offline.
Yeah. All right, let's thank the speaker again. The next talk will be given by Fabian Zeisser, who will tell us about incremental computation for efficient programmable inference in probabilistic programs.
Yeah, thanks. Hi, I'm Fabian Zeisser.
Sorry. So let me try again. In computer science, we often have an expensive function that we want to evaluate on many inputs. And in fact, these inputs are often related, so we can compute the outputs more efficiently than by evaluating the expensive function from scratch. And that's what the field of incremental computation is about. For example, the input may be a database, and the expensive function could be a database query. After making a small change to the database, such as inserting, deleting, or modifying a single row, we don't want to redo the whole computation, but we only want to do the necessary work to update the output. And what's more relevant to the session is that the same pattern shows up when inferring the distribution of a probabilistic program. The inputs are program traces, and the expensive function is the density evaluation according to the probabilistic program. Inference algorithms like Markov chain Monte Carlo make small changes to the trace, such as changing a parameter, inserting a cluster, making a Gibbs move, etc. By the way, if you don't know these concepts, I'll explain them in a minute. But here as well, we want to compute the new density functions, density values incrementally. In fact, this is critical for scalable inference. Typically, if you naively evaluate your densities, your inference algorithm will scale quadratically in the size of the data. But by only recomputing what's necessary, you can get it down to linear running time. You could achieve this by writing your inference algorithm by hand, but that is difficult and error-prone. So what we'd like to do is, for our probabilistic programming systems, to automate this. And indeed, many existing probabilistic programming systems do actually provide some form of incremental computation. These incrementalization schemes can be fairly complex. For instance, some of them construct elaborate dependency graphs, and since we're dealing with probabilities, even the existence of nodes in the dependency graph can be random. Such complexity makes this prone to bugs that may even result in wrong inference results. And in many cases, existing systems are still asymptotically slower than a manual implementation. To address this, our main idea is to reduce the problem to deterministic incrementalization. So we first transform our probabilistic program to a deterministic program for the density function, and then incrementalize this deterministic program. This means we can build on all the research done on incremental computation outside of probabilistic programming, and in addition, this modularity simplifies reasoning about our approach. We make contributions to both this density transformation and the deterministic incrementalization transformation. But before I get into the details of our approach, let me give you a concrete example. Suppose you're given a set of data points and you want to find clusters in them. One possible approach is to reason about how the data may have been generated. And for that, we're going to use a probabilistic program. A probabilistic program is an ordinary program extended with the ability to draw random values from a distribution. So given a number n of data points to generate, this program first samples the number of clusters from a geometric distribution, written with a tilde. And behind the scenes, the probabilistic programming system collects all the random choices in a data structure called the trace. For example, when this line of code is executed, the system might sample 4 as the number of clusters. I'll also visualize this trace on the top right as we step through the program. The clusters are represented by these blobs. Next, the program samples parameters for each cluster. The mean determines the location and the covariance, the size and shape. Then it samples a weight for each cluster. A higher weight means that more data points belong to this cluster. Using these weights, each data point is assigned to one of the cluster indices. For instance, the first data point is assigned to cluster 1 in blue. Finally, we loop over all the data points and sample a random location based on the parameters of the assigned cluster. Different executions of this program can lead to very different traces with a varying number of clusters. Obviously, our goal is not just to generate random data sets or random traces, but to infer the clusters given a set of points. So if we're given these data points, we want to find program executions that could plausibly have generated them. In other words, we want to find plausible execution traces where the data part is exactly the given data points. A very popular and effective approach for this is our Markov chain Monte Carlo algorithms. And what they do is they essentially search for good traces. And I'm going to show you how this works in a slightly simplified and sped up way. We start with an arbitrary initial trace with the fixed data points. And typically this will be a bad explanation of the data, like here. Next, the algorithm makes changes to the trace, such as reassigning data points to different clusters, or changing the cluster parameters, or splitting a cluster, and so on. And in this way, it constructs a chain of traces whose distribution converges to the posterior distribution of the probabilistic program, conditioned on the given data points. Now let's look closer at how the traces in the chain are sampled. So starting from the initial trace, we consider a set of proposals for the next trace. Here, the proposals are different cluster assignments. The programmer can specify these proposals or fall back on default proposals by the probabilistic programming system. Next, we score each proposal using the density function of the probabilistic program. High density means that the trace is plausible or likely to have been generated by the program. And based on these densities, one proposal is accepted as the next element of the chain. And then we keep going the same way. We start with this trace, and this time the proposals change the cluster parameters. The proposals are again evaluated by the density function, and one of them is accepted, and so on. For all of these proposed traces, we essentially have to rerun the probabilistic program to evaluate the densities. And we have to do this at every step of the inference. So this dominates the running time of the inference algorithm. But note that all the proposed traces are very similar. They only differ in their cluster assignments on the previous slide, or in the cluster parameters, as we see here. So we can save a lot of time if we can find a way to compute the density incrementally. So coming back to our main idea, we have two program transformations. The first one turns a probabilistic program, which generates traces, into a density function, which evaluates traces. The second one turns any deterministic program, for instance, a density function, into an incremental one, which can efficiently process input changes. And when we combine these two transformations, we can incrementally evaluate densities and speed up inference. Let me first discuss the incrementalization. So what are the key ideas? We're going to build our approach on ideas from the incremental lambda calculus. This calculus is a formal framework for incremental computation in functional languages. And a key idea is to make changes to values explicit in the language. Every type tau has an associated change type delta tau, which represents changes to values of type tau. And these change types are defined recursively on the type grammar. There are many ways of choosing concrete change types, but for our setting, we found that the following choices worked well. I'll explain them in a second, but first, some motivation. Why did we pick these? Well, the change type is supposed to track what has changed about a value so that we can avoid unnecessary recomputation. For example, when we loop over a collection, like a list or a map, it is crucial to know which elements of the collection have changed so that we can skip loop iterations for unchanged elements. This can lead to asymptotic speedups, which is why our change types for collections are very fine-grained. For instance, the change type for a map data structure records removals, modifications, insertions, and insertions of elements. The change type for records is a subrecord, which is like a record of changes, except unchanged fields may be omitted. By contrast, knowing exactly how a real number has changed typically doesn't help you avoid a lot of work, so we use a simpler coarse-grained change type for base types, like booleans. For these, we just record the new value and whether it changed at all. Furthermore, in the incremental lambda calculus, every primitive function, such as arithmetic operations or list operations, all of them have incremental versions operating on change types. And these incremental primitives serve two main purposes. First, they precisely propagate change information. They describe how the output value changed given changes to the input. Second, they aim to exploit the change information to avoid redundant work when recomputing the output change. The overall program transformation then stitches these incremental primitives together and ensures that all the changes are propagated downstream to exploit opportunities for incrementalization. What do these incremental versions of a function look like? Well, a couple of versions have been proposed in the literature, but they all have some serious drawbacks. So in the original incremental lambda calculus, a function f has a derivative delta f from an original input and an input change to an output change. This serves the purpose of propagating changes forward, but a big downside is that only some derivatives are efficient to compute. When the input change alone determines the output change, then f is called self-maintainable and the derivative is efficient, but most functions are not self-maintainable. And that's the motivation for a version of the incremental lambda calculus with caching. So the caching version of a function returns the output and in addition a cache of intermediate results. The derivative now also takes in a cache and outputs an updated cache. This allows it to be more efficient and also works for functions that are not self-maintainable. It creates another problem though. The composition of two functions needs the caches of both individual functions. So we quickly end up with huge caches everywhere whose types depend on the implementation of f and not just its type. All of that is cumbersome and complicates correctness proofs. We address these problems with an abstraction called updaters. So we model updaters as a co-inductive type that sends input changes to output changes, plus a new updater for subsequent changes. Concretely, an incremental function takes an input and produces an output, but in addition, we get an updater. That updater, in turn, accepts changes to the input and produces changes to the output, as well as another updater. And this updater takes input changes on top of the previous change and produces output changes on top of the previous output change, and so on. How do the updaters work on the inside? To construct them, you provide an initial cache value, and an update function from an input change and a cache to an output change and an updated cache. And when you apply an updater to an input change, it forwards that change together with the cache to the update function, and constructs a new updater from the new cache and the same update function. As a concrete example, let's consider the incremental version of the length function for a list. So this function returns the length of the list, and it constructs an updater whose cache is the length using the makeUpdater construct. The update function accepts an input change and the cached list length. And the new length is just the cached length plus the number of inserted elements minus the number of removed elements. And finally, it returns the change value for the length, which contains the new value and a flag indicating whether it changed, and also the new length as the new cache value. So in summary, the updaters encapsulate their cache types, and we can still stack changes on top of each other, which is important for probabilistic inference. So now let me put all the pieces together and summarize how the incrementalization transformation works. We start with a deterministic function from an input type to an output type, and such a deterministic program is incrementalized to a function that takes the same input type, but in addition to the output also produces an updater. A lot of this was inspired by the literature on the incremental lambda calculus, but our approach also works in the typed higher order setting. Each primitive operation in our language has an incremental version, and our program transformation composes them together. And since we have a higher order language, we can treat loops as a special higher order primitive, where the loop body is an argument. The incremental versions skip loop iterations by caching intermediate results, and our other primitives are designed to propagate precise change information about collections, so that when we get to a loop that iterates over such a collection, we can save a lot of work. And this is what leads to our asymptotic efficiency gains. Now let me quickly talk about the density transformation. It transforms a probabilistic program into a deterministic program, taking a trace as input and producing a result value and the density for this trace. The basic idea is that sampling from a distribution is transformed to evaluating the density function of the distribution at the corresponding element of the trace. For example, if we have a program sampling x and y from two distributions, the density program will take the values for x and y from the trace and compute the density of the value for that distribution. All of these subdensities are multiplied together and returned as the total density together with the result. Such a transformation is standard in the probabilistic programming literature, but in our setting, things are a bit more interesting because we support unordered collections and unique name generation. If you want to learn more about how we do this, come talk to me afterwards, or you can also read the paper. But I want to quickly explain the motivation for the existence of these features. Having types for our traces with a rich structure is important because when we incrementalize the density function, it will work on a richly structured change type for traces. This way, we can have concise descriptions for lots of changes, like removing a cluster. In fact, the notion of trace types has been described before, but our trace types are more expressive. So how do we assign a type to the traces of a program? The idea is to mirror the control flow that generated the trace. For example, a sequence of sample statements has a record type, recording the type of each subtrace. Iterating over a list produces a list of subtraces, and in our work, we added unordered iteration, say over a set of names, which produces an unordered map from names to subtraces. Why does our language have fresh name generation? This is also motivated by our desire to keep changes concise. To see why, consider the clustering example again, where we index clusters as 1, 2, 3, and so on. Now suppose we delete cluster 1, which yields a new trace below. Then all the assignments have to change, because all the other indices are shifted down by 1. And this destroys incrementality. Instead, if we give each cluster a fresh name or ID, things work out much better. The assignments are now a list that assigns each data point to the name of a cluster rather than an index. And now if we remove a cluster, this only affects the data points which were assigned to that cluster, and the rest is unchanged. Okay. All of this was to explain the compositional approach to incrementalization. But a key property of our approach is that we can prove correctness properties. So we proved both stages of our transformation correct. And thanks to working in the typed setting and our updater abstraction, we were able to use denotational semantics and logical relations arguments in the proofs. We also implemented our techniques in Julia and evaluated it for a number of inference programs and models. Specifically, we compared our implementation with full recomputation and the experimental fine-grained incrementalization in the GEN system. And we evaluated several MCMC inference programs on a variety of models. And in the plots, you can see that our method in blue is faster than the other methods, and the running time grows more slowly in the size of the data. The takeaway is that our method is the only one achieving the same asymptotic running time as a manual implementation for all these benchmarks. And you can find more details in the paper. Speaking of the paper, there's a lot of cool stuff that I didn't have time to talk about, both for incremental computation people and for probabilistic programmers. And yeah, this concludes my talk. Thank you very much.
All right, any questions? Maybe I have one quick one.
Yeah.
So you mentioned probabilistic programs or programs with sampling instructions. Do you also consider conditioning?
The conditioning is not an explicit operation in the program. It's rather that once the program is written, we constrain the traces to the program. For example, I had this. This is going to take a bit. But basically, the idea is that we fix the data part of the trace here. And yeah, only. But this is not in the program directly. This is constrained afterwards. Yes.
But it's implicitly.
Yes.
All right. Thank you. If there are no more questions, let's thank Fabian again. Gradient estimation as probabilistic inference. Just turn on the mic as well.
Testing. Okay. All right. Hi, I'm Gaurav. I'm a second-year PhD student at Carnegie Mellon University, and I'll be talking about a new approach to this problem of gradient estimation, which is essentially about differentiating probabilistic programs. So in standard automatic differentiation, we take a user-written program which implements a mathematical function, for example, theta squared plus 1, and produce a new program which computes its derivative, for example, 2 times theta. And modern tools for automatic differentiation, which are very widely used, have taken this basic idea and extended it to programs featuring loops, mutation, arrays, and so forth. And the basic idea here is to take an input program T, which denotes a mathematical function, and synthesize a new program T prime, which denotes its gradient. But what happens if our input program features probabilistic constructs? So on the left here, I have a probabilistic program which samples from distributions, such as a Bernoulli distribution and a Gaussian distribution. In this setting, every time I sample from my program, I may get a different value drawn from some underlying probability distribution. So how can we usefully generalize automatic differentiation to this setting? Well, an observation we can make here is that although each individual sample here may not be differentiable, the expectation of these samples may very well be. So for example, for this program here, we can actually write out its expectation symbolically as a function of theta. And this is a perfectly reasonable function to differentiate with respect to theta. But there's a catch here, which is that for a general probabilistic program, it is completely unreasonable to hope to be able to calculate its expectation in closed form efficiently. And so it is similarly unreasonable to hope to be able to compute its gradient exactly. So we have to relax our goals slightly. And instead, let's ask for a new program T prime which unbiasedly estimates the gradient of this expectation. So this new gradient estimator program will be a new program which we can sample from, just like the original program, but with the key property that the expectation of samples drawn from this new program T prime is equal to the gradient of the expectation of samples drawn from the original program. So gradient estimation is very broadly applicable. It's useful whenever you want to optimize or compute sensitivities of a probabilistic model with respect to its parameters. And indeed, over the decades, gradient estimation has found use in a wide range of fields, including queuing theory, biochemistry, neural networks, and so forth. So in the work I'm presenting today, we present a new approach to this problem of gradient estimation called gradient inference. And gradient inference has two main goals. The first is to unify existing gradient estimators. So over the past few decades, a wide range of existing schemes have been developed, including pathwise estimators, score-based estimators, phantom estimators, and so forth. And gradient inference aims to provide a common mathematical framework in which we can express and connect these different schemes. The second, and probably most important goal of gradient inference, is to enable the design of new gradient estimators. So when dealing with unbiased estimators, the name of the game is lower variance. And as a practitioner, applying gradient estimators to challenging applications, often your bottleneck is the high variance of your estimators. So gradient inference aims to synthesize new gradient estimators that are lower variance than the state of the art. So how do we accomplish these two goals? The key idea is to convert a gradient estimation problem into a probabilistic inference problem. So probabilistic inference is in the title of the session and has been quite well studied in programming languages. And the key idea here is rather than treating gradient estimation as a wholly new problem to solve from scratch, we'd like to be able to leverage the rich existing infrastructure for probabilistic inference to improve the design of gradient estimators. And our approach is automated in a new programming system called gradinf. So for concreteness, let me give you an example. So in queuing theory, the flow of packets in a network queue is often modeled as a stochastic process in time, where packets either enter or leave the queue. And so by sampling many random trajectories from this process, we can estimate the expected number of packets in the queue after a certain number of events. And of course, this expectation will depend on our model parameters. So if we, for example, increase the arrival rate of packets, then the distribution and the expectation unsurprisingly shift upwards. And in this setting, a natural question to ask is what is the sensitivity of this expectation to the arrival rate of packets? And this is precisely a gradient estimation problem. So let's see how gradinf attacks this problem. The first step is to rewrite this queuing model as a probabilistic program. So this is a model that is parametric in the input parameter we want to differentiate with respect to, and from which we can sample different outputs. So now, rather than trying to synthesize an entire gradient estimator program in one fell swoop, what gradinf does is it synthesizes the so-called inference target program. So this is itself an ordinary probabilistic program, which means it can be targeted with well-understood methods for probabilistic inference, such as importance sampling, stratification, sequential Monte Carlo, and so forth. And so in gradient inference, we actually synthesize a gradient estimator program by applying standard libraries for probabilistic inference and automatic differentiation to this inference target. So a theme that may have been apparent in the previous slide is that gradient inference is fundamentally compositional. So the input to gradinf is a higher order functional probabilistic program. To synthesize the inference target you saw in the previous slide, gradinf applies program transformations for coupling and for factorization, which are two variance reduction techniques that are baked into the inference target. Finally, existing inference and AD methods are applied to form a sound gradient estimator. So before I dive into some of the key details here, I want to give you a preview of the payoff. So for the queuing model I defined, gradinf can both express existing state-of-the-art estimators, such as score-based estimators and phantom estimators. And moreover, by swapping out the probabilistic inference algorithm used in the phantom estimator for one based on exact variable elimination, gradinf can achieve a 100 times variance reduction. So now that I've given you a preview of the payoff, let's discuss some of the key ideas in gradient inference, starting with coupling. So coupling is an idea that's found use in programming language literature, mostly for proving properties of probabilistic programs. But let's see why it's also useful for gradient estimation. So on the left here, I have the target gradient of an expectation that we're interested in. And on the right, assuming for simplicity that we have a real valued parameter, I've written just like the Calculus 101 expression for this gradient as a limit. And what I want to draw your attention to is that the numerator here is a difference of an expectation evaluated at the original program and an expectation evaluated at the perturbed program with parameter theta plus epsilon. And the existence of this difference of expectations motivates the formation of a coupling. So the key idea behind decoupling is that if I have two random variables, one distributed according to the original program, XA, and another distributed according to the perturbed program, XB, then by linearity of expectation, the expectation of XB minus XA will always equal to this target difference irrespective of our choice of joint distribution. And so we can choose this joint distribution to minimize the variance of our difference estimator. And this choice of joint is precisely the notion of a coupling. So in GradInf, we apply a coupling program transformation to our input program T to produce a new program C of T from which we can sample pairs of values, with the property that if I sample a pair XA, XB from our program, then XA and XB are guaranteed to be marginally distributed as we desire. And so I'll direct you to the paper for the full details of this transformation, but I want to give you an example of how it works on a flip primitive. So in the flip primitive, we accept a probability and flip a weighted coin, returning true or false randomly. At the type level, the coupling of this primitive now accepts two probabilities and returns a coupled pair of booleans. And on the right here, I have one example of a sound coupling that fulfills this type. So this coupling accepts a common random number omega and thresholds it against both of the input probabilities to form a coupled pair of booleans. So once we've defined the coupling transformation on each probabilistic primitive in our language, it automatically synthesizes couplings of arbitrary input programs. So on the right here, I'm showing the coupling of the queuing model program from before. And so this is a program that operates on pairs of values. And for those familiar with the notion from relational proof logics, this program can be understood as a probabilistic product program. Let's move on to the next step in gradient inference, which is factorization. So recall that once we formed this coupled program, we're interested in the expectation of this difference estimator, XB minus XA. And a classic variance reduction technique we can apply here is to condition this estimator on some information F, which by the Tower property of expectations is guaranteed to preserve unbiasedness, but also gives a provable variance reduction. So we'd like to apply this variance reduction technique to form better gradient estimators, but there's a question, which is what information should we condition upon? And the key idea here is to set F to the random value sampled in the fragment of our coupled program, which computes only the first component of coupled pairs. So let's see how this affects our coupling primitives from before. On the left here, I'm showing the common random numbers coupling of a flip primitive. And on the right, I'm actually showing the exact same coupling denotationally, but written such that we first sample the first Boolean, and then sample the second Boolean conditionally upon the first Boolean. And so this is a factorization of the original coupling. But we'd like to be able to surface this factorization structure at the type level. And so we have a type system wherein those random choices which determine the first component of coupled pairs are annotated as primal, and the remaining choices are annotated as residual. And what's lurking underneath the surface here is a non-interference property, where residual random choices are prohibited from affecting primal random choices. And so this type system is based on generalizing the classic dependency calculus of Martin Abadi with probabilistic constructs. So in gradient inference, the way we exploit this new factorization structure is by forming a partial evaluation of our original coupled program in the following sense. All of the primal random decisions which determine the first component of coupled pairs are made to be deterministic based on a fixed random seed, while all the remaining residual choices are left untouched. And to summarize what we've done here with coupling and factorization, we've synthesized an inference target program whose expectation is precisely this coupled and conditioned difference estimator we wanted to form. So now the role of probabilistic inference will be to efficiently estimate this expectation. And to give you some motivation for why probabilistic inference may be useful here, observe that only those coupled traces where XA and XB differ actually contribute to this expectation. And so the role of probabilistic inference here is to sample those coupled traces where the event XA not equals XB holds. And one reason why probabilistic inference is especially useful here is recall that XA and XB are drawn from very similar programs. One was the original program with parameter theta, and the other was the program with parameter theta plus epsilon. So as epsilon goes to 0, the probability they differ actually, with many couplings, will go to 0 as well. And so probabilistic inference can give a substantial variance reduction here. The final step of gradient inference, after having baked in all of these variance reduction techniques into this difference estimator, is to convert this difference estimator into a gradient estimator by applying standard automatic differentiation methods. So I'll direct you to the paper for details on our soundness arguments, but I'll just remark that like the gradient inference pipeline itself, our soundness proofs are compositional, and to push our proofs through for higher order probabilistic programs, we make use of quasi-Borel spaces and proof-relevant logical relations. To conclude, I'll demonstrate some of the applications of gradient inference. We consider a few in the paper. So in mathematical finance, practitioners care a lot about measuring the sensitivity of the prices of options to model parameters. And in this setting, GradInf is able to synthesize gradient estimators with asymptotically lower variance with respect to simulation time. Another important application of gradient estimation is in biochemistry. So on the left here is a reaction network model, and these models are often used to model processes such as gene transcription in the cell. And in this setting, GradInf is able to facilitate significantly faster inference of optimal model parameters when used in stochastic gradient descent. We also studied the expressivity of gradient inference in the paper. So we showed that a number of existing gradient estimators can be expressed compositionally by combining different factorized couplings with different probabilistic inference algorithms. And to conclude, our contributions are a new mathematical framework for gradient estimation, which we call gradient inference, a system which automates gradient inference called GradInf, soundness proofs, and a demonstration of substantial variance reduction. And finally, if you're encountering challenging gradient estimation applications in your own research, I'd encourage you to reach out because maybe gradient inference can be of use. Thank you very much.
All right, questions? I have perhaps a naive question. So if we write a probabilistic program, how do we know whether the gradient of the expectation of its output is well defined?
It's a good question. So in our soundness arguments to the first approximation would sort of be our approach is correct, assuming it exists. So we don't, that would be a property which you need proof logic. So there's also been a lot of work on like smoothness tracking, and it is a tricky problem to verify that for sure. There's other works which do that.
So there do exist methods which focus on checking whether a gradient of the expected value exists.
So for example, I think Alex, your ADAP paper would provide a certificate which would, as a corollary, verify that property. Is that fair to say?
Yeah, or it gives you a verification condition.
Yeah. Okay. Yeah.
Thank you. Any other questions?
Hi, great talk. I really enjoyed it. So back to one of the applications, I think the second application, were you learning some of these parameters like alpha, beta, and stuff?
I wasn't clear about that. So this is a parameter inference application.
Parameter inference, yes.
We have a loss, so it's not a Bayesian setting, so it's a bit of a heuristic loss to define the parameters which best fit the data. And we're using our gradient estimators to determine the optimal parameters.
I see, so the gradients are used to search for those parameters. Okay, sounds good. Thanks so much.
Just a curiosity, since you mentioned it, how do you use the proof-relevant logical relation? Is that for the information flow part or no?
No, it's used even for the proof of the soundness of our coupling calculation. So let me go back to, so we want to show that for any input program, input term of any type, its coupling belongs to some coupling logical relation. And it turns out that I think the inductive step for probabilistic buying, you want to be able to access the quasi-Borel space morphism, which pushes
Okay, thanks. We have time for one more question. Yep.
Hi, really great, really good talk. My question is it possible to apply this algorithm in reasoning about parametric family, like the distribution's parameter is not certain? So it's possible to reason about this?
Yeah, definitely. Are you thinking of, like, for example, like maximum likelihood estimation?
Yes, yes,
Yeah,
yes.
definitely. Then if you're doing that in a gradient-based way, or you're doing something Bayesian and you want, well, Bayesian is a bit trickier because stochastic gradients are a bit tricky, but definitely for like maximum likelihood estimation, it's immediate how to use gradients. Also for variational inference.
I
So
see.
yeah, in all those settings, gradients.
Like the robustness of the probabilistic programming.
Sorry, can you say that again?
Like the robustness of the Bayesian programs.
Yeah, it could probably be used for robustness in
I
the right
see.
conditions.
Thank you.
Okay, let's thank Gaurav again.
That's probably just mine that I left there. I don't think it's oh, okay. I'll just use the keyboard. All right. Okay. Hello, everyone. My name is John, and I will be telling you about this categorical semantics for probabilistic symbolic execution. I just want to start by giving some background on this term right here, probabilistic symbolic execution. So probabilistic symbolic execution is a probabilistic inference technique that's based on kind of repurposing a symbolic executor to do probabilistic inference. This was originally introduced in the software engineering community in the early 2010s, repurposing the symbolic pathfinder to do reliability analysis, and has been kind of gaining traction in the PL community recently with recent papers repurposing symbolic execution frameworks like CLE and Rosette to do probabilistic inference. The kind of idea that underlies all of these works is that there's this structural similarity between symbolic execution on the one hand and probabilistic inference on the other. So ordinarily, right, we think of symbolic execution as this procedure that takes ordinary execution and lifts it to operate on these symbolic values. And by the same token, probabilistic symbolic execution is kind of a repurposing of this inference strategy that lifts execution to operate on random variables instead. Just to give you a taste for what this looks like, here's a probabilistic program that I've written in a recently introduced probabilistic programming language called Roulette. So this is a recursive function that simulates a random walk for n steps, one-dimensional random walk. And the way you want to read this is that it kind of recursively computes a random variable. So in the base case, when the number of steps is 0, it returns this deterministic random variable at 0. And then in the inductive case, it uses this flip instruction to generate a fresh Boolean random variable to decide which direction to step in. Then based on the outcome of that fresh Boolean random variable, it uses kind of arithmetic on random variables in order to compute the result of the walk recursively. Obviously, random variables don't exist on the computer, and so what's really happening under the hood is that symbolic execution is working very hard to kind of compute symbolic representations of these random variables. In particular, all of the language constructs that are used to define this function are kind of lifted to operate on these symbolic variables, right? So this if here is not an ordinary if, it's a lifted if. These are kind of lifted integers, and these are lifted recursive procedures. Okay, so for the purposes of this talk, there's a couple important points I just want to emphasize about this symbolic execution technique. So first, as you can probably already see, it's really different from ordinary execution. Okay, so with this program, you kind of have this highly non-standard reading of the program in which everything is lifted to operate on these random variables. What this means is that it's often very tricky to reason about the precise performance characteristics of these programs. And you often need to know kind of low-level details of the implementation in order to know whether the program you've written will actually perform inference efficiently.
it's often difficult to prove these implementations sound. So speaking from personal experience here, I was working on this roulette programming language I just mentioned, and even though there was kind of this existing formal framework for doing semantics of symbolic execution, we weren't able to adapt that framework to do probabilistic inference. And so what we ended up doing is kind of redoing the semantics of the underlying symbolic executor as well as the correctness proofs. Okay, so that kind of brings me to the point of this work, which is, can we introduce new semantic domains that make it easier to design, reason about, and verify these probabilistic symbolic executors? And the main idea of this work is essentially to provide a mathematical analog of a symbolic executor. Just as a symbolic executor kind of lifts all of the ordinary language constructs to operate on symbolic variables, what we want is a semantic domain that lifts all mathematical objects to operate on symbolic mathematical objects. And this is where kind of the categorical and categorical semantics comes in. So category theory is one of these tools that excels at building these non-standard models or mathematical universes, in part due to its concept of universal construction. Right? So if we look at kind of ordinary set theory, category theory provides a way of encapsulating the standard constructs of set theory in the form of abstract definitions that can be then reinterpreted in other settings. For example, the kind of standard Cartesian product of sets, function space of sets, are encapsulated categorically in this statement that the category of sets and functions is Cartesian closed. Similarly, the existence of objects like the set of lists and things like index products and coproducts correspond to certain completeness and co-completeness properties. And so what we do in this work is essentially we build multiple categories with analogous structure that provides a kind of semantic analog or symbolic analog of these set theoretic constructions. And in doing so, we obtain a kind of symbolic set theory in which you have these same kind of set theoretic constructions, but they have a symbolic flavor. Now, the symbolic set theory, of course, is not the ordinary set theory we're familiar with. And so inside of this kind of new universe of symbolic sets, we get access to new constructions that didn't exist before, which are particular to probabilistic symbolic execution. All of these constructions we kind of package up in what we call a symbolic meta-language, which can be used to quickly give symbolic semantics and prove correctness. Concretely, we build 3 new categories using kind of off-the-shelf tools from categorical semantics, which provide kind of concrete models of this symbolic meta-language I just gestured at. We build a new category of symbolic sets, which I call a synset, for building symbolic semantics. We build a mergeable analog of this category for talking about a technique called type-directed state merging. Then we build a category of what we call instantiation structures for proving the correctness of any of the symbolic semantics constructed in this way. Okay, so let me describe each of these kind of semantic domains in turn, starting with SymSet. So the basic idea kind of underlying this category of symbolic sets is that it's an abstraction or axiomatization of an old kind of purely functional denotational model of symbolic execution, which was recently made precise, in which a symbolic value kind of denotes a function that's parameterized by concrete instantiations for all the symbolic variables. Let me just illustrate this with an example. So suppose I have a really simple program here. I'm just going to say let x equal the result of flip 1/2. Now operationally, what a probabilistic symbolic executor does when given this program is it just generates a fresh symbolic variable, say alpha, to represent kind of the result of that flip. But what we can do is we can think about this kind of denotationally as a function that takes in models or concrete instantiations for all the symbolic variables that have been generated so far and spits out a concrete Boolean. This function in particular is the one that's defined by cases, returning true on kind of the subspace of this space of models in which alpha holds, and returning false on the complementary subspace in which it doesn't. What's interesting about this kind of functional view of symbolic values is that these symbolic values can become more precise when they flow under different branches. For instance, suppose that I take this value x, and then I perform an if on it. Then what a symbolic executor will do is it will evaluate both branches of this if, and on each branch, the symbolic value x kind of behaves as if it was either true or false. From the functional point of view, this is captured by the notion of restriction. So on the then branch, when x holds, we can think about this function x
as being restricted to the blue subspace on which alpha is true, leaving behind this kind of partial function with domain alpha that's constant at true. Conversely, on the else branch, we can think about x as being restricted to the complementary orange subspace, leaving behind this partial function only defined on that subspace and constant at false. So this is kind of the key idea behind our definition of the category of symbolic sets. Basically, we take this notion of restriction and like the path-sensitive nature of symbolic values, and we axiomatize that in the form of an abstract definition. Formally, we say that a symbolic set consists of two things. First, an assignment from path conditions to sets which abstract over these collections of functions with domain phi. Second, for each strengthening of a path condition from, say, phi to phi prime, a function that sends these kind of abstract functions with domain phi to abstract functions with the stronger path condition. This is kind of like an abstraction of this operation of restricting a function to a smaller domain. This restriction operation is then subject to a couple of laws which ensure that it actually behaves like function restriction. In particular, if I take a function and I restrict it to its domain, that should do nothing. And if I take a function and I restrict it twice, then that should be the same as restricting by the intersection. Examples of symbolic sets include, of course, functions with the right domain, but also many other things, such as formulas with the restriction operation defined by conjunction, and also stores defined as mappings from variables to formulas, with the restriction operation kind of defined variable by variable. Now, what makes this definition categorical is that that elementary definition I just showed you can actually be repackaged in the form of a functoriality condition. So if we think about like a picture of a symbolic set, you can see that it kind of defines a mapping from path conditions to sets. So for each path condition phi, you get a set hat x sub phi. And for each strengthening of a path condition from phi to phi prime, you get a function from x sub phi to x sub phi prime. We can make this precise by taking all the path conditions and packaging them up into a category that we call P. Then we can redefine symbolic sets to just be a functor from this category P to the category of sets. The assignment from phi to x sub phi then becomes the action of this functor on objects. The restriction map becomes the action on morphisms. And these laws that I stated earlier become the functoriality laws. The advantage of this kind of crisper, more abstract definition is that it immediately places symbolic sets in the context of a whole category of symbolic sets, namely the category of functors from this category P to set. Now we're really off to the races because this category is a well-known form of category called the category of presheaves. That makes this category of symbolic sets that we've introduced an instance of a well-established recipe in categorical logic called presheaf semantics. Many books have been written already on presheaf semantics, and so we're basically allowed to kind of import all of that machinery wholesale to kind of complete our universe of symbolic sets with a rich collection of universal constructions. Concretely, we kind of obtained this symbolic meta-language that I was gesturing at earlier, which includes features like simply typed lambda calculus, algebraic data types with pattern matching, and monadic do notation for working with these special monads that we introduced for symbolic execution. The result is that we can essentially take simple type theory as a meta-language for building symbolic semantics. For example, suppose we want to make a probabilistic symbolic executor for this imperative language. What we can do is we can first write a monadic definitional interpreter for this language, which just looks like an ordinary interpreter. In particular, the interpretation of sequencing can be given by ordinary monadic bind, and the interpretation of if can be given by ordinary if. But then what we do is, rather than reading this interpreter in the normal way, we're going to reinterpret this interpreter in the category of symbolic sets that we just constructed. Once we do that and unfold all of the definitions, out comes a symbolic semantics that captures kind of all the details of symbolic execution that we would need to do to perform probabilistic inference on this language. In particular, if we kind of quickly zoom in on the semantics of if here, you can see that the symbolic semantics computed in this way tells you that you have to maintain a path condition, and then to symbolically evaluate the if, you should evaluate the guard to get a formula, conjoin that formula onto the path condition used to evaluate the branches, and then combine the results of evaluating those branches. In fact, this definition contains enough operational detail that you can essentially just transcribe it into code. So here I've just taken that math on the previous slide and I've turned it into a Haskell interpreter that actually does perform probabilistic symbolic execution for the imperative language I showed earlier. Okay, so just summing up here, we've introduced this category of symbolic sets, which is kind of like a lifted set theory that is a nice home for symbolic semantics. And we introduced a meta language that allows us to take definitional interpreters and automatically get symbolic semantics for a language of interest. Finally, the symbolic semantics that we get out, even though they're denotational, are kind of informative and executable. They contain enough detail to be turned into reference interpreters. Okay. The second thing I want to talk about is that we also introduced a category for talking about a technique in symbolic execution called state merging. This category we call the category of mergeable symbolic sets. To give some context for state merging, I want to just consider this simple program here. So this program takes flip and it does something rather unusual with it, which is that it branches on there and then in each branch it just returns that variable unchanged. Okay, so based on what we know about symbolic execution, this program will turn the flip into a symbolic value, which kind of represents this function that we saw earlier. Then, symbolically executing the if will restrict this function to the blue and orange subspaces on both branches, leaving behind these kind of partial functions. Now, a traditional symbolic executor would kind of continue to evaluate both branches, leading to a duplication of work. And so the purpose of state merging is to take these two values and combine them into a single value, intuitively performing the union of functions, leaving behind a single function that summarizes the result of both branches. So once again, what we do is we axiomatize this kind of abstract operation of union, providing a mergeable analog of symbolic sets. So whereas symbolic sets kind of axiomatize this restriction operation on functions, our category of mergeable symbolic sets axiomatizes this operation of disjoint union. And again, we kind of make contact with categorical machinery here. In this case, we use this idea that the union operation, like this equation that goes from a combination of functions defined on subspaces to a function defined on the whole space, is kind of like a passage from like a local function to a global function. This function defined on the blue subspace is local to the subspace alpha, function on the orange subspace local to its complement, and then the merge kind of amalgamates these into a global operation. It turns out that topologists have thought very hard about this kind of passage from local to global. And so we're actually able to reuse this abstract concept of sheaf in this context to capture the notion of state merging. Starting from this intuition, we kind of build this like dictionary between symbolic execution and sheaf theory. The kind of space of models that I've been drawing as a picture corresponds to what is traditionally a topological space. Path conditions correspond to open subspaces, and this merge operation corresponds to the amalgamation operation that turns out to be key to defining the notion of sheaf. Formally, we can define the category of symbolic sets to be this subcategory of SymSet consisting of those pre-sheaves that are sheaves. This makes mergeable symbolic sets an instance of what is known as sheaf semantics, which, like pre-sheaf semantics, also kind of has received extensive treatment. And so just like with the category of symbolic sets, we obtain a kind of mergeable analog of our symbolic set theory that automatically understands state merging. In particular, if we take this definitional interpreter for our imperative language from earlier, and we reinterpret it in the category of mergeable symbolic sets, then we automatically attain a symbolic semantics with state merging. Zooming in on if, for example, you can see that the semantics of the symbolic if is going to take the stores produced by both branches, and it's going to use this square cup operation to combine them. This merge operation is defined not uniformly, but rather in a type-directed manner, which can be calculated from the universal constructions that are available in the category of sheaves. For example, if we look at a collection of merge operations for different types, you can see that the merge operation for the singleton symbolic set is defined to return the singleton element. Merge operation on formulas is defined in the usual way, and the merge operation on pairs is defined pointwise. What I find especially nice about this is that the kind of sheaf theory provides an abstract characterization of many real implementation details. For example, suppose we want to calculate the merge operation on lists. It turns out that if you take the formula for computing list objects in a category of sheaves, and you unfold all the definitions, you get this merge operation, which says that lists should be merged by length, which turns out to be exactly how state-of-the-art implementation like Rosette merges lists. Okay, so just taking stock here, we kind of made contact with sheaf semantics, and that allowed us to give a denotational explanation of real state merging code alongside this kind of topological perspective on symbolic execution with state merging. All right. I just want to quickly talk about the final part of what we did, which is we introduced a new semantic domain for talking about correctness. So this semantic domain is an instance of the same recipe I've been describing so far. We took a kind of classic definition of correctness, which says that a symbolic execution should simultaneously simulate the results of ordinary execution on all instantiations for symbolic variables, and we abstracted it to work in the categorical context. For this abstraction, the key thing is to note that whereas ordinary execution runs one input at a time, symbolic execution runs simultaneously many inputs parameterized by a model M for all of the symbolic variables. Now, in order to specify correctness for the symbolic semantics, the key thing to formalize is this notion of instantiation, what it means to take a symbolic value and specialize it against a concrete model. And so just as the categories of symbolic sets and mergeable symbolic sets axiomatize restriction and union of functions, we introduced this third category of instantiation structures that axiomatizes function application. It turns out that, once again, we have the ability to use categorical machinery in this context, whereas symbolic sets and their mergeable counterpart correspond to pre-sheaves and sheaves. This category of instantiation structures corresponds to a technique called gluing, which you may have heard in the previous talk in the form of proof-relevant logical relations. Using this, we give a model of symbolic set theory that understands this notion of instantiation and prove a general theorem that says that any definitional interpreter written using the symbolic metalanguage is automatically correct. And I want to emphasize that this theorem works no matter whether the semantics is using state merging or not, and it generalizes to the probabilistic context, and it makes use of a kind of compositional notion of correctness. Okay, there's more details in the paper, which I invite you to check out if you're interested. And I just want to quickly say that in future and ongoing work, we're thinking about trying to mechanize a lot of these things in a proof assistant to make them a bit more accessible, and also to try and connect the abstract theory we've developed to low-level implementations. Okay, that's all I have.
We have time for one or two questions.
Thanks for your talk. I'm just curious how this would work with like equivalence. So like maybe let's say you have two programs which are like have the same expected value, have the same like distribution of outputs, I guess. Would they have the same categorical semantics, or like to what extent would they be the same?
Yeah, that's a good question. The symbolic semantics that you get kind of captures the behavior of an implementation. So there are going to be certain programs whose symbolic semantics will differ because their symbolic execution will differ. So for example, you could have one program that computes a distribution using 2 flips and another computes the same distribution using 3. Those will have different symbolic semantics. But you will be able to prove, using our framework for correctness, that both of those symbolic semantics kind of refine the same distribution, or ground truth semantics.
Can you replace set with something else?
Yes, yes you can. The framework is quite general, and you can replace set with
relation.
It would have to be a category that satisfies certain universal properties, which I don't have the list of on hand, but yes, you could.
Okay. Thanks.
Yeah.
All right, if there are no more questions, let's thank John again. This was the last talk of the session. Thank you.
Ooh, okay. Welcome to the last session of PLDI. This is the potpourri session. We've got 2 exciting papers during this session. So let's go ahead and get started with our first talk, which is by Eden Frankel. Take it away.
Thank you. Thank you. I'm Eden. Thank you for being here. So in this talk, I'm going to explain to you a way to write safety proofs. Which use simpler formulas than if you were to trying to prove safety using just an inductive invariant. And I'm going to do so by leveraging ideas about forward-backward symmetry of safety proofs and a notion of prophecy. So when we're given a safety verification task, we're given a system over some state space, and we have some initial states of the system, some bad states that we do not want the system to reach, and a set of transitions. And specifically in this work, we consider systems specified in first-order logic. So the initial states and the bad states are given using first-order logical formulas, and the transitions are given using a transition formula over 2 states. And our goal, when given such a safety verification task, is to prove that there is no error trace of the system. So there is no sequence of steps leading from an initial state to a bad state. And the traditional way to do this is to find what we call a safe inductive invariant. So this is an inductive invariant, which means it's another formula which describes the sets of states that contains all of the initial states. And if you begin a transition within this inductive invariant, you remain inside this inductive invariant. And it is safe, meaning that it excludes all of the bad states that you do not want to reach. So this is the traditional way to do this. And when we're operating in the setting of first-order logic, then these conditions can be verified using an SMT solver. Now, the problem with using a safe inductive invariant may be that when the systems become complex, the safe inductive invariant becomes complex. So for example, here you have an example of part of the inductive invariant for Paxos, and you can see that it's complex both in terms of the kind of Boolean structure that the formula has. So it has conjunctions and disjunctions, and also, perhaps more importantly, in terms of the quantification. So a lot of quantifiers and quantifier alternations and quantifier nesting. And these 2 sources of complexity mean that when we are trying to write a safe inductive invariant for this kind of problem, we need to consider a large candidate space for possible invariants. So either manually or using an automatic technique trying to find a safe inductive invariant. And additionally, when we want to check a candidate invariant, we need to perform complex SMT queries that may involve a lot of quantifiers. So the idea in this work is to prove complex properties such as the invariant I showed you before, but by breaking them down into simpler incremental steps. And specifically, we do this by proposing a proof system for safety, which incorporates 2 main ideas. So the first idea will be incremental forward-backward reasoning. And I will show that this allows us to use formulas with a simpler Boolean structure. And the second component will be a notion of prophecy, which will result in formulas with a simpler quantifier structure. So let's begin with the forward-backward reasoning. What do I mean by forward-backward reasoning? So let's say we have this kind of safety problem, and before I showed you that we can find perhaps this kind of safe inductive invariant. This is an invariant in the forward direction, right? It's an over-approximation of the reachable states. We could have proven safety equivalently using a backward inductive invariant. So an invariant which includes all of the bad states and is preserved backwards in time. And if this kind of invariant excludes all of the initial states, then the system is safe. But let's say these kinds of invariants are too complex for us to express, and we want to use simpler reasoning, but we allow our proof technique to use incrementality. So let's say, what does it mean that we want to use simpler properties? So let's say we have a formula which is not expressive enough to express exactly the safe inductive invariant that we want to find, but expresses some simpler property which holds on all reachable states. So this is an inductive invariant which is not sufficient for proving safety, but it is simpler to express. So we have not managed to prove safety, but we have excluded some of the bad states, and we can now continue the proof incrementally. So we can now ignore all of the bad states that we have already managed to exclude, and maybe now we can find a backward inductive invariant with respect to the remaining bad states. And now we managed to exclude some of the initial states, effectively proving that these cannot lead to bad states. And maybe now we complete the proof by finding a third, simpler formula, which shows that these initial states cannot lead to bad states. So intuitively, why is this proof of safety? Well, you can think about this kind of proof as accumulating properties of error traces, right? In each step, we added either a forward inductive invariant or a backward inductive invariant, which proves the property of error traces. And if we manage to exclude either the bad states or the initial states, then we have managed to prove safety of the system. Well, we can now ask whether if we have this kind of proof, could we just have used an inductive invariant, and what would it look like? And we have a theorem in the paper that shows that if you have a forward-backward proof, there always exists a safe inductive invariant, which is a Boolean combination of the formulas that you use in the forward-backward proof, but this inductive invariant may be more complex, so it may include more conjunctions and disjunctions. So for example, the forward-backward proof that I showed you before, the invariant would look something like this. So you can see that if you were trying to find a safe inductive invariant for the problem, it would have been more complex in terms of its Boolean structure than the incremental proof. Well, and we also show in the paper that there are problems where this simplification is strict. So the forward-backward proof is able to use simpler formulas than the safe inductive invariant that is required to prove safety. Which means that we can sometimes use this technique to simplify the Boolean structure of formulas that we check inductiveness for and that we search for when searching for a proof. Now, of course, we're operating in the setting of Ursula logic, so the obvious question is, can we use this to reduce the kind of quantification in formulas? And the answer is partially. So we saw before the forward-backward proof that resulted in this equivalent safe inductive invariant, which means that, for example, if these formulas were universal formulas, then the resulting inductive invariant would have included 3 quantifiers and one of them an existential quantifier. So if the formulas that we use in the forward-backward proof contain quantification, we may have reduced the number of quantifiers that we need in a formula, in each formula used in the proof. But remember that we can always convert any forward-backward proof into a safe inductive invariant, which is a Boolean combination of the formulas that we use, which means that we cannot ever reduce the kind of quantifier nesting or alternations that we use just by using forward-backward steps. Because otherwise, we would have been able to, because such a formula cannot be broken down into a simpler Boolean structure. So, for example, if we want to prove that all error traces satisfy this property as part of our incremental proof, we cannot hope to do so in several steps. We must do it in one step. So the question is now, what can we use to reduce the quantifier nesting and alternations? And perhaps unsurprisingly, we use ideas from prophecy, a notion of prophecy, to simplify this quantifier structure. So let's look at an example. The main idea is to replace quantification with explicit prophecy witnesses. So let's say you want to prove this kind of property. You want to prove, as part of your incremental proof, that every error trace satisfies this quantified property that says that there exists some x that satisfies p, and for all y, q of x, y holds. Well, maybe you can add some witness symbol, w, and prove in the forward direction that it satisfies p. And then after adding this kind of witness, you prove in the backward direction a backward inductive invariant that for this w, which satisfies p, the universal property holds that for all y, q of w, y holds. And you have effectively proven the quantified property that for every error trace, there exists some x that satisfies p and the universal property. And you have done so in 2 steps instead of 1, and used fewer quantifiers and fewer quantifier alternations. Now, of course, the question is, when does it sound to do this first step, to add some witness satisfying p? And as an example, consider a situation where you can prove that in every initial state there is some element satisfying p, and that p is a property that is preserved for any element in a transition. In that situation, you can add this kind of assumption to your about error traces to your proof. And you can ask that question more generally. So when is it sound to add a witness satisfying some property to to the properties that you have accumulated about error traces. And in the paper, we characterize this as a safety problem. So as another safety problem that if you prove its safety, this means that you are allowed to add this kind of prophecy. And intuitively, we do so by introducing a monitor relation that keeps track of possible witnesses and making sure that this relation is never empty. And now you can use a separate safety proof to prove that this prophecy is sound, and then you can continue with your incremental proof. Now, in practice, a lot of the times, these kinds of soundness problems have a very particular structure, so we develop heuristics for example, what kind of invariant do you usually need to prove soundness of prophecy, which is what we use in practice in the case study that I will talk about soon. Now the question is, again, we have this kind of incremental proof that uses prophecy and forward-backward iterations. Can we just use a safe inductive invariant? And the answer is yes, but this time this inductive invariant will include more quantifier nesting and alternations. So at a very high level, why this happens is that you have some proof of the soundness of the witness that has some quantifiers, and then you have the remaining incremental proof that contains more quantifiers, and when you construct the inductive invariant for the original problem, you get these quantifiers nested under each other. And this gives you the kind of nesting that we saw before. Very similar to the example that I showed you before. And this similar to forward-backward iterations, this can sometimes be used to reduce the kind of quantifier nesting and alternations that you need to use in formulas. So this culminates in a proof system for safety problems where every statement is a safety problem, and we have rules for introducing inductive invariants, for performing incrementality, and for introducing prophecy, where you see in the prophecy rule, for example, you need to prove the soundness of the prophecy and continue the incremental proof in the other premise. And the rule for time reversal to take advantage of the forward-backward symmetry. And we show in the paper, as I showed you here, that this kind of proof using these rules can be converted into a safe inductive invariant for the original problem, but that using more rules means that you will get a more complex safe inductive invariant using the construction that I showed you before. Okay. We have implemented a proof checker for this system in the MyPyV tool. So instead of writing like a proof tree that looks something like this, you can write the forward-backward iterations and introducing the prophecy in something that looks more like this. And we constructed manual proofs for 12 Paxos variants and Raft. And we compared the three possible proof methods for these variants. So the first method is just the forward inductive invariant that is used to prove safety, the traditional method, and then a proof system that only uses forward-backward iterations, a proof system and then the complete proof system that also uses prophecy. And we compare the kind of formula complexity that you need to use in order to prove safety for each of these proof systems. So I'm not going to go over the full case study, but here's some illustrative examples. So the proof for Paxos includes an invariant that looks something like this. So it has these quantifiers and quantifier nesting and alternations, and also a Boolean structure that contains both conjunctions and negations and disjunctions. And if you try to prove the same example using forward, backwards, and prophecy, then you can replace this kind of invariant with witnesses for some of the quantified variables. Of course, you need to prove the soundness of adding these witnesses using some more formulas. And then you can do a backward iteration with a simpler formula and a forward iteration with a simpler formula. And you can see that, and this effectively replaces this kind of invariant in the proof of safety for this example. And you can see that the formulas that we had to use, that the user had to provide in order to complete the proof, are much simpler. They contain only universal quantification and are clausal in form. And I refer to the paper for the full case study. So to conclude, I presented the proof system for incremental safety proofs, which incorporates both forward-backward reasoning. This allowed us to simplify the kind of Boolean structure in formulas, and prophecy and soundness, and prophecy and the soundness formalization characterization of when is it sound to add prophecy, which allowed us to simplify the quantifier structure in formulas. And we saw that using more proof rules means that the formulas that you have to use in proofs become simpler. We have implemented this in a proof checker and conducted a case study, and we think that one of the most interesting directions for future research is to try to automate proof search in the system, and hopefully, because we need simpler formulas, this will mean that automation will find proofs faster or more easily. So thank you, and I'm happy to take any questions that you might have.
We got time for questions.
So I know prophecy variables from simplifying proofs in distributed systems and concurrency in general. And there usually what happens is that you don't know whether some event is going to happen in the future. And so you by having a prophecy variable that predicts whether it'll happen or not, what usually happens is that you have these two distinct scenarios about the future, whether the linearizability point is going to be now or later or something like that. You can decide based on the future, right? But I get a sense that this is not the sense in which your prophecy variables are. So is this a more general notion of a prophecy variable, or can you describe what intuitively a prophecy variable, why does it simplify a proof?
Yeah, so the name prophecy here may be slightly confusing. So this is a kind of prophecy. It can also, in some contexts, be a kind of a combination of history and prophecy. So this kind of prophecy doesn't necessarily talk about something that is decided in the future, maybe. Basically, it allows you to talk about the kind of things that have to happen on an error trace. So, for example, if you have a distributed protocol that some decision happens at some point, and your invariant would usually say something like, maybe there exists some quorum where this decision was accepted, then your witness for this quorum will witness this, will be the one that performed this decision. So in that sense, it's something that happens in the future, but it's a bit our formalization. If you return to our formalization of how we introduce witnesses, we say that we have this characterization that proves that the witness that there is a witness for every error trace that satisfies this property. So this is the kind of requirement for the prophecy. But this is the only requirement. So maybe this witness is in the first step, or maybe it's in the 100th step. But all we prove is that on every error trace there is this witness. So it can happen at any point in the trace. Yeah.
So it looks very different from the ones.
Yes, it has similarities and differences. I think that it's not a generalization, but it has intersections with other notions of prophecy. Yes.
Thank you.
Okay, great. We still have time for another question. Okay, so I have a question about this future work direction. So, you have more proof rules here, right? But is there some sense in which the simplification of the individual proofs is amenable to proof search? Have you experimented with this at all?
Yes. So, as you say, now we have simplified the kind of formulas that we need, but we have complicated the proofs in terms of the structure that they may have.
Yeah.
So we have in mind a form of proof automation which we think works well for the forward-backward part. So you can think about just performing forward iterations and backward iterations, alternating these if you just have forward-backward steps. And we have good intuitions as to why this will be a good tactic for proof search. Mm-hmm. The real difficulty is to know when to introduce prophecy. What kind of prophecy do you need to introduce? And this is harder to automate, and yeah, so this is the main challenge when you want to automate this kind of thing.
Do you feel like as you did case studies with this that you developed intuitions for how to come up with those prophecies?
Yeah, so we have good intuitions
as
to what kind of prophecy we need to introduce for these examples, but of course we don't know how well this generalizes for other examples.
Yeah.
The forward-backward automation seems to general as well, because just basic observations about the kind of formulas that you need. But yeah.
Okay. Great. Let's give the speaker another round of applause. Next paper is an UPLA 2025 paper presentation by Celeste Barnaby on active learning for neurosymbolic program synthesis.
Hello. Okay, great. Okay. Hi, everyone. I'm Celeste Barnaby, and I'm going to be talking about our paper, Active Learning for Neurosymbolic Program Synthesis, which appeared at UPSLA last year. So neurosymbolic learning is a paradigm that combines the flexibility of neural networks with the precision of symbolic reasoning. In particular, neurosymbolic programming languages use neural models to process unstructured data like images or text, and symbolic constructs to reason over the resulting predictions in a compositional and interpretable way. So let's look at this example of a neurosymbolic domain designed for image editing and search tasks. So here we have this user who has a travel blog where they share images from their camping trip. And while they're working on a blog post about their gear, this user wants to include some cropped images of people wearing backpacks. So manually searching through their library of thousands of photos would obviously be very, very tedious. So instead, the user provides a few examples of the types of cropped images they want, and a synthesizer learns an image editing program that can automatically process their entire image collection. Importantly, these programs combine neural perception, like detecting people in backpacks, with symbolic spatial reasoning over the detected objects. So here, this program finds all people in an image whose bounding boxes contain backpacks, and then applies a crop action to those people. So under the hood, we give the annotated images provided by the user to a synthesizer, which generates programs consistent with these examples. However, there may be multiple programs that match the examples while behaving differently on other inputs. So the key challenge becomes, how do we determine which program the user actually wants? Prior work in synthesis has aimed to address this issue through active learning techniques that query the user to clarify ambiguities. For instance, an active learning procedure may ask the user to annotate an additional image in their library. This additional input-output example may then allow the system to rule out programs in the hypothesis space and identify the user's intended program. However, when applied to neurosymbolic settings, active learning techniques may inadvertently return an unintended program. To see why, let's consider this example provided by the user, where the input is this image on the left and the desired output is the cropped image on the right. To check whether a candidate program matches this example, the synthesizer first applies a computer vision model to detect objects in this input image. However, these models are imperfect. And in this case, the model detects the person, but misses the backpack. As a result, this program incorrectly produces a null output and is pruned from the hypothesis space, even though it actually matches the user's intended task. To address this issue, we use conformal prediction to explicitly model uncertainty in neural predictions. So instead of producing a single prediction, conformal prediction returns a set of plausible predictions that contain the true label with high probability. In this example, the model confidently detects the person, but is uncertain about the backpack. So standard inference would discard this low confidence prediction, causing the correct program to be pruned. In contrast, with conformal prediction, we can consider a range of confidence scores for which the detected object may or may not exist. In this case, conformal prediction may allow us to determine that the backpack may or may not exist in the image. Since the model is uncertain about whether the backpack exists, we can think of this image as having two different versions, one where the backpack does exist and one where it doesn't. We can collect these versions of the image into what is called a prediction set. In the context of neurosymbolic learning, we can use this prediction set to define conformal semantics for programs, such that every program returns an output set that is very likely to contain the ground truth label. So here, the output set contains a null value for the version of the image where the backpack doesn't exist, and a cropped image for the case where the backpack does exist. When we check whether this program matches the user's I/O example, we can check whether the user-provided output is contained within the output set. In this case, the correct cropped image is contained in the output set, so we wouldn't prune this program, which is what we want. When using conformal semantics, active learning becomes even more critical because the flexibility of returning a set of outputs can lead to an explosion in the number of potential solutions. A neurosymbolic synthesis problem can admit an intractable number of programs consistent with the conformal semantics. Neurosymbolic active learning refines the hypothesis space by asking questions that reduce ambiguity in the conformal prediction sets. So these questions target two distinct sources of ambiguity. First, ambiguity about the user's intended program, which we address by asking the user for additional input-output examples. And second, ambiguity about the ground truth labels of inputs, which we resolve by asking the user for specific ground truth labels in images. We can continue asking questions until there's no remaining ambiguity in the hypothesis space. So at a high level, our active learning loop repeatedly asks questions that refine both the hypothesis space of programs and the conformal prediction sets. In each round of active learning, programs are eliminated from the hypothesis space, either because the user provides new examples or provides a new ground truth label, which narrows down an output set. After refining the hypothesis space, we can check whether it's been fully disambiguated. If it has, we terminate active learning and return some program. If not, we select a new question to ask the user. So this work has three main contributions. First, we propose and formalize the neurosymbolic active learning problem. Second, we introduce constrained conformal evaluation, which allows us to reason soundly about uncertainty in neural predictions. And third, we implement these ideas in a tool called Smart Label. So let's walk through an example of all of these steps. I'm going to use a running example in a simple visual arithmetic domain, where here the goal is to synthesize a program that counts the number of digits greater than 5 in a list of handwritten digit images. The DSL combines standard symbolic operators like map and filter with a neural perception operator, 2-digit, that classifies the digit images. In this example, the user labels this input list with output 2, since only 6 and 7 are greater than 5. However, the neural model misclassifies the second digit as an 8, so the correct program incorrectly evaluates to 3 and is pruned from the hypothesis space. This is exactly the kind of neural uncertainty that we want active learning to reason about. With conformal evaluation, we instead maintain prediction sets that capture the model's uncertainty about the second and third digits. As a result, this program now produces an output set containing both 2 and 3. Since the user's label is contained in this output set, the correct program is retained in the hypothesis space. However, under conformal semantics, many other programs may also remain consistent with the user's example. So here, let's suppose that our hypothesis space contains these 4 candidate programs. We want to determine which of these programs matches the user's intent. So given this hypothesis space, the next step in our active learning procedure is distinguish. The goal of the distinguish procedure is to determine whether 2 programs could produce different outputs under some assignment of the ground truth neural labels. In this example, the first program has output set 2, 3, while the second has output set 1, 2. So since there exists some labeling of the uncertain digits for which the programs produce different outputs, these programs are distinguishable and there's still ambiguity in the hypothesis space. So because of that, we continue to question selection. In the question selection step, we consider 2 kinds of questions that ask the user for outputs on new inputs, or questions that ask the user to label uncertain neural predictions. In this example, suppose our question space contains just these 2 label queries. Our goal is to select the question that eliminates as many candidate programs as possible. But since we don't know ahead of time how the user will answer the question, we select the question whose worst answer will prune the most programs, and we refer to this as the question's pruning power. To determine the pruning power of the first question, let's look at what will happen depending on how the user answers the question. So if the user labels x2 as 0, then we remove 8 from x2's prediction set, which means that the first program couldn't output 3, the second couldn't output 2, and the third couldn't output 1. Since 2 is no longer in the second program's output set, we would prune this program, since it doesn't match the user's given output. We use the same process to see what will happen if the user answers 8 instead. In this case, we find that the second and third programs will be pruned. So the worst answer of this question is 0, because it will lead to 25% of programs being pruned. Hence, the pruning power of this question is 25%. Meanwhile, the worst answer of the second program is 9, which will cause 0 programs to be pruned. Hence, we see that the first question is the better one to ask the user, because even in the worst case, we'll still prune 25% of programs. So after asking this question and receiving the answer 0, we now refine the hypothesis space. This is similar to how we check a question's pruning power, except now we have some definitive new information from the user. So since we know that x2 is 0, we know that we can safely prune the second program. A key challenge of this active learning framework is the overhead of conformal evaluation, because naively it would require enumerating all combinations in the Cartesian product of the prediction sets of an input. Since the number of combinations grows exponentially, this quickly becomes an intractable problem. To address this, we introduce an efficient constrained conformal evaluation procedure based on bidirectional abstract interpretation. The idea is to propagate constraints both forward and backward through programs in order to prune infeasible elements of prediction sets early. Let's look at an example. So here's the AST of a program that counts the number of digits less than 4 in a list. We want to know whether this program's output set contains 2 without having to enumerate all possible combinations of labels. First, we begin abstract interpretation at the leaf node of the AST. The leaf node annotation is an abstraction of the conformal prediction results, with each prediction set abstracted by an integer interval containing all the elements of the prediction set. The abstract value of the next internal node is obtained by applying an abstract transformer for the filter operation. So the question mark after the second interval indicates that this item may or may not have been filtered, depending on whether its value is actually above or below 4. Finally, we annotate the root node with the abstract output of the program, which is the integer interval ranging from 1 to 2, depending on whether there are 1 or 2 items in the list. So now we perform backward reasoning, starting from the output to tighten these annotations. To start, we can tighten the root node annotation to the interval containing just the user's output value. So we know that the program outputs 2, and in order for that to happen, that means that exactly 2 items must have been filtered. So this second item that we were uncertain about must not have been filtered. Since this item must not have been filtered, we can infer that its value must have been less than 4, so we can restrict this interval to 0, 3. And now, when we perform conformal evaluation, we can disregard items in prediction sets that don't match these inferred conditions. So in this case, we can throw out the 8 in the second prediction set. This means that we now only have to consider 2 options instead of the 4 we originally had. So now that I've discussed the core technical contributions of our approach, I'll share some details of our evaluation. We evaluated our tool Smart Label on 3 neurosymbolic domains: image editing, image search, and the visual arithmetic domain that we've been looking at. In total, we evaluated 112 synthesis tasks. Each task included a fixed input space, question space, and hypothesis space of programs. Across domains, tasks contained roughly 200 inputs and 800 questions on average. To construct the initial hypothesis space, we sampled 2 input-output examples and performed synthesis up to a fixed AST depth. The resulting hypothesis spaces contained roughly 1,500 candidate programs on average. To evaluate the accuracy of Smart Label, we compared it against 2 active learning baselines from prior work, SampleSci and LearnSci. Because these approaches do not model uncertainty, they may incorrectly prune the ground truth program from the hypothesis space. Across all benchmarks, Smart Label achieves 98% accuracy compared to 65% for SampleSci and 58% for LearnSci. Next, we evaluated how many rounds of user interaction Smart Label requires to identify the correct program. We compared our worst case pruning objective against 2 alternatives, optimizing for the expected pruning power and selecting questions uniformly at random. Overall, our strategy requires the fewest rounds of user interaction, converging in roughly 5 questions on average. Finally, we performed an ablation study where we used a naive version of conformal evaluation that doesn't use our forward-backward abstract interpretation approach. And we found that this ablation roughly doubled the average time of interaction. So to conclude, Smart Label uses targeted active learning queries to eliminate ambiguity in neurosymbolic synthesis tasks while reasoning soundly about neural uncertainty. More broadly, we think that active learning is a promising way to make synthesis systems more reliable and trustworthy in practice. So thank you, and I can take questions now.
Okay, questions?
So I'm surprised you needed an abstract interpretation for the CCE, the Is that CCE?
Yes.
Yeah. Can't just SAT solver do it? I presume these are small programs. The SAT solver should be able to figure out whether there exists an interpretation of each of them in the set such that it evaluates correctly.
You're proposing using a SAT solver instead of abstract interpretation?
Yeah, or an SMT solver, yeah.
For the visual arithmetic domain, like it's pretty simple, but for more complex domains like the image-based domains, it was more complex.
I see, okay. And your abstract interpretation is for those domains as well?
Yeah, so to instantiate Smart Label on a specific domain, we require the user to provide like an abstraction with forward and backward transformers.
Okay.
Okay, more questions?
Hi. So if I understood correctly, the questions you ask are mostly about the labels and the uncertainty that comes from the neural model. Do you sometimes ask questions that kind of, combine separating multiple symbolic parts of the program and the neural programs together? Like, could there be a question that slices both of them?
Okay, so we had two types of questions. A question could ask you about a specific object where there's uncertainty and ask you like, is this actually a backpack? Or it could ask you, like give you a new image and ask you to perform your desired edit. You're proposing something that kind of combines those two.
I guess, I'm asking if that's possible. Or
It is possible. For an interactive tool, we wanted to make sure that the questions were like realistically simple for a user to be able to answer accurately. But I think that is an interesting space for future work to explore other types of questions that you could ask.
Thank you.
Okay, more questions? So I have maybe a more curiosity-based question. When you talked about the metric for whether it's a sort of a strong question, that sort of reminded me of sort of like an information theoretic interpretation of this, that you want to reduce uncertainty the most. Like what's the most informative question that you can ask? Have you thought of an information theoretic interpretation of that aspect of your mechanism?
We did not think about it from an information theoretic perspective, at least I didn't. That's interesting. Yeah, an important principle is that as you answer each question, you're like making progress, like you're eliminating at least some programs from the hypothesis space. So that was our framework.
Yeah, in information theory, it tends to be more of a continuous, like you're updating your posterior distribution based on the questions, so that might allow you to also get rid of the sort of, actually, I mean, another question I have is how do you choose the threshold at which sort of the uncertainty counts as, like your example was if it was 20%, it was counted as not, and 70% was.
Yeah, that's a great question. So that's we use like existing conformal prediction approaches for that. So the threshold is learned from a calibration set of labeled data with respect to a specific coverage rate provided by the user. So like the user provides the calibration data set and says, I want to make sure that the prediction sets contain the ground truth with at least 99% probability. And you can learn the threshold based on that. And like intuitively, the tighter your bounds, the bigger the prediction sets will be.
Okay, great, thank you. All right, if there's no more questions, we can wrap up this talk. Thank you. So that's the end of this particular session, but PLDI, some of the other sessions in parallel are still ongoing, so if there are talks there, I encourage you